Welcome back to Whispering Universes, where we explore the silent wonders hiding in plain sight across our solar system, waiting patiently for us to understand their stories. Tonight we turn our attention not to the volcanic fury of Io or the fractured ice shell of Europa, but to two worlds that have stood quietly in Jupiter's shadow for billions of years, bearing witness to the entire history of our solar system while keeping their deepest secrets locked beneath ancient, cratered surfaces. Ganymede and Callisto, the third and fourth of Jupiter's Galilean moons, the outermost members of that miniature solar system orbiting our largest planet. These are not small worlds. Ganymede exceeds Mercury in diameter, making it the largest moon in our entire solar system. Callisto follows close behind, nearly as large, nearly as massive, nearly as mysterious. Both are bigger than Pluto, bigger than all the asteroids combined, substantial worlds that would count as major planets if they orbited the Sun independently, rather than circling Jupiter in its distant realm. Yet these giants remain quiet in our collective imagination. When we speak of the Galilean moons, we often lead with Io's volcanoes erupting hundreds of kilometers into space, or Europa's subsurface ocean that might harbor life. Ganymede and Callisto seem, at first glance, less dramatic, less urgent, less deserving of our attention. Their surfaces show none of Io's constant transformation, none of Europa's youthful cracks and ridges. They appear ancient, stable, finished with their geological stories. But this appearance deceives. Beneath those quiet exteriors lie worlds of profound complexity and surprising revelations. Ganymede, despite its heavily cratered surface, possesses something no other moon in the solar system can claim. Its own magnetic field, its own magnetosphere, a bubble of magnetic influence carved out within Jupiter's overwhelming magnetic environment. This alone tells us that Ganymede's interior remains active in ways we're still working to understand, that processes we associate with planets, not moons, continue deep below that ancient ice. And Callisto, which appears to be nothing more than a frozen archive of impact events, stretching back 4 billion years, the most heavily cratered surface we've ever observed, preserving a record of the early solar system's violence that has been erased everywhere else. This ancient witness also hides an ocean. Not at its surface where we might expect it, not in a nicely differentiated interior like Europa's, but somehow maintained within a body that never fully separated into distinct layers of rock and ice. How does such an ocean exist? What keeps it liquid? These questions remain open, inviting, mysterious. The story of these two moons is the story of patient observation revealing unexpected complexity. It's the story of worlds that don't shout for attention, but reward careful study with profound insights into how moons form, how they evolve, how they maintain hidden oceans, and what makes each world in our solar system unique, despite surface similarities. Tonight, we'll explore these quiet giants together. We'll trace the history of their discovery, from Galileo's first telescopic glimpses to the detailed reconnaissance of spacecraft missions. We'll understand what makes Ganymede magnetic and active, despite its age. We'll learn how Callisto preserves a surface older than anything we can see on Earth, while hiding liquid water beneath. We'll consider what these worlds tell us about the formation and evolution of the entire Jovian system. And we'll look forward to upcoming missions that will study these moons with unprecedented detail, seeking to answer questions we've carried for decades. As you settle in, perhaps already feeling your breathing slow, your thoughts beginning to drift, imagine standing on the surface of one of these distant moons. The sky above you is dominated by Jupiter, that massive sphere covering a significant portion of the heavens, its bands and storms visible even from this great distance. Around you stretches an ancient landscape of ice and rock, craters large and small, telling stories of impacts that occurred when life on Earth was just beginning. Beneath your feet, hidden kilometers down through layers of ice, an ocean moves in total darkness, kept liquid by processes we're only beginning to comprehend. You stand on a world both ancient and active, quiet but complex, a giant that has waited billions of years for someone to truly see it. Let's explore these patient giants together, here on Whispering Universes, and discover why the quietest voices sometimes have the most profound things to say. On the evening of January 7th, 1610, in Padua, Italy, a mathematician named Galileo Galilei pointed a newly constructed telescope toward Jupiter and saw something that would change human understanding of our place in the cosmos forever. What he observed wasn't Jupiter itself, that bright wandering star known since prehistoric times, but three small points of light arranged in a line near the planet. He noted their positions carefully, as any good observer would, and returned to his telescope the following night. The points of light had moved, not randomly, but in a pattern that suggested they were somehow connected to Jupiter, orbiting the giant planet just as the Moon orbits Earth. Over subsequent nights, Galileo observed a fourth point of light joining the others, and watched as all four moved in their regular patterns, sometimes disappearing behind Jupiter or in front of it, sometimes appearing on one side and then, nights later, on the other. By January 15th, just over a week after his first observation, Galileo had sufficient data to conclude something revolutionary. Jupiter had moons of its own. The Earth was not unique in having a satellite. The celestial spheres were not all centered on our world. Among those 4 points of light, moving in their stately dance around Jupiter, were the two worlds we'll focus on tonight. Ganymede, the largest, orbiting Jupiter every 715 days at a distance of just over 1 million kilometers. And Callisto, the outermost of the four, completing its orbit every 16.69 days at a distance of nearly 2 million kilometers from Jupiter's cloud tops. Galileo couldn't see any details of these worlds, couldn't discern that they were spheres rather than points, couldn't measure their sizes or compositions, but he could see that they moved, that they obeyed mathematical laws, that the universe was more complex and less Earth-centered than anyone had imagined. The philosophical implications cascaded through European thought. If Jupiter could have moons, then the ancient model of crystalline spheres, all rotating around Earth, made no sense. If moons could orbit Jupiter while Jupiter orbited the Sun, then the Copernican model of a sun-centered solar system suddenly seemed not just mathematically convenient, but physically real. These tiny points of light, visible only through the new technology of the telescope, became crucial evidence in a transformation of human self-understanding that we're still processing more than 4 centuries later. Galileo initially called his discoveries the Medicean stars, hoping to curry favour with his patron, Cosimo II de' Medici, Grand Duke of Tuscany, but this name didn't persist. Instead, they became known as the Galilean satellites, honouring their discoverer. The individual moons themselves received names suggested by Simon Marius, another astronomer who claimed independent discovery around the same time. Marius drew the names from Greek mythology, specifically from figures associated with Zeus, the Greek equivalent of the Roman Jupiter. Ganymede took its name from a beautiful youth in Greek mythology, a Trojan prince whom Zeus found so attractive that the god transformed into an eagle and carried Ganymede to Olympus to serve as cupbearer to the gods. Callisto's name comes from a nymph, one of Artemis's hunting companions, whom Zeus seduced and who was subsequently transformed into a bear and placed in the heavens as the constellation Ursa Major. These mythological names, with their stories of transformation and divine attention, seem appropriate for worlds that would eventually reveal transformations of their own and reward our detailed attention with unexpected discoveries. For more than 3 centuries after Galileo's observations, these moons remained points of light. Better telescopes revealed more detail, showed their disks as tiny circles rather than mere points, allowed measurements of their sizes and orbital parameters with increasing precision. But they remained fundamentally mysterious, distant worlds about which we could make educated guesses, but claim little certain knowledge. The patient giants orbited, neither asking for nor receiving much attention compared to the planets themselves. They were curiosities, certainly, important proofs of Copernican astronomy, useful tools for determining longitude at sea by timing their eclipses behind Jupiter. But what they actually were, what their surfaces looked like, whether they had atmospheres or magnetic fields or geological activity, all of this remained speculation based on limited data, waiting for the technology that would eventually carry our instruments across the solar system to see these worlds up close. Imagine Galileo, eye pressed to his simple telescope on those cold January nights, carefully sketching the positions of those tiny lights, not yet knowing their names or their true nature, knowing only that he was seeing something important, something that would matter. The universe was revealing itself to be larger, more complex, more full of worlds than anyone had imagined. Among those worlds were two giants that would wait nearly 4 centuries more before beginning to reveal their secrets in detail. As telescopes improved through the 18th and 19th centuries, the Galilean moons gradually resolved from dimensionless points into tiny disks, allowing astronomers to measure their apparent sizes and, knowing their distances, calculate their actual diameters. By the mid-1800s, observers had determined that Ganymede and Callisto were both enormous moons, comparable in size to the planet Mercury, far larger than Earth's moon. This immediately raised questions about their composition and formation. How could moons grow so large? What were they made of? The development of spectroscopy in the late 19th century offered a new tool for understanding distant worlds. By analysing the light reflected from an object, astronomers could determine something about the materials on its surface. Early spectroscopic observations of the Galilean satellites proved challenging. These were small, distant targets whose reflected sunlight had to be separated from the overwhelming glare of Jupiter itself. But persistent observation gradually yielded results. By the 1970s, ground-based spectroscopy had revealed strong evidence for water ice on the surfaces of Ganymede and Callisto. The spectral signatures were clear, absorption features at specific wavelengths that matched laboratory measurements of ice. This was a profound discovery, though perhaps not surprising given their distance from the Sun and the cold conditions at Jupiter's orbit. These were worlds whose surfaces consisted, at least partially, of frozen water, fundamentally different from the rocky surfaces of the inner solar system planets, and more akin to the icy bodies of the outer solar system. The presence of water ice immediately suggested lower densities than purely rocky worlds. Density measurements, derived from observations of how these moons gravitationally affected each other and Jupiter itself, confirmed this expectation. Ganymede's density came in around 1.94 grams per cubic centimetre, substantially less than rocky bodies like the Moon, 334 GSM3, or Mercury, 5.43 GSM3, but more than pure water ice, about 0.92 GSM3. This indicated a mixture, substantial rock in the interior, but also significant amounts of ice, perhaps half the total mass or more. Callisto showed a similar pattern, but with an even lower density, 1.83 grams per cubic centimetre, suggesting an even higher proportion of ice to rock. These measurements told a story of formation in the cold outer regions of the solar nebula, where water could condense and accrete into growing moons, along with silicate rock and perhaps some metallic iron. These were not the rocky, metal-rich worlds of the inner solar system, but hybrid bodies, half-frozen ocean worlds, half-rocky planets, something in between. Ground-based observations also revealed differences in surface brightness between the two moons. Ganymede appeared brighter, more reflective, suggesting cleaner or fresher ice on its surface. Callisto appeared darker, its surface ice apparently contaminated with darker materials, perhaps rocky dust brought up from impacts, or perhaps organic compounds created by radiation, processing of surface ices over billions of years. These brightness differences hinted at different surface histories, different rates of geological activity or resurfacing. Telescopic observations through the mid-20th century also tracked changes in the Moon's appearances as they orbited Jupiter, revealing that they were in synchronous rotation, always keeping the same face toward Jupiter just as Earth's Moon does toward Earth. This synchronous locking results from tidal forces over millions of years, gradually slowing a Moon's rotation until its rotational period matches its orbital period. The discovery confirmed that these moons had been in their current orbits long enough for tidal forces to completely dominate their rotational evolution. Some observers reported what they thought might be subtle variations in surface features, possible evidence of active geology. These observations were at the very edge of what ground-based telescopes could resolve, and many remained controversial. Were there really darker and lighter regions on Ganymede's surface? Did Callisto show any variation at all beyond its generally dark appearance? The human eye and brain, staring at a tiny shimmering disk through layers of Earth's turbulent atmosphere, could play tricks. What was real and what was artifact remained unclear. What these centuries of patient observation from Earth revealed was that Ganymede and Callisto were substantial, ice-rich worlds, different from anything in the inner solar system, but also different from each other in subtle ways that ground-based observations could only hint at. To truly understand these moons, to see their surface features, to measure their magnetic fields and thin atmospheres, to probe their interior structures, would require sending spacecraft across the gulf of space to Jupiter itself. As the space age dawned in the late 1950s and 1960s, mission planners began seriously considering how to reach the outer solar system. Jupiter, with its miniature solar system of large moons, represented an obvious target, a destination that could teach us about planetary formation, about the conditions in the outer solar nebula, about how worlds evolve in the cold darkness far from the sun's warmth. Among those worlds, the quiet giants Ganymede and Callisto waited, ready to reveal complexities that no ground-based telescope could anticipate, ready to surprise us with magnetic fields and hidden oceans and surface features that told stories stretching back to the solar system's formation. In December 1973, Pioneer 10 became the first spacecraft to reach Jupiter, streaking past the giant planet at a distance of about 130,000 kilometers from the cloud tops. The encounter lasted only a matter of hours, but in those hours, Pioneer 10's instruments gathered more data about Jupiter and its environment than all previous astronomical observations combined. Among its targets were the Galilean moons, though the trajectory didn't allow close approaches to any of them. Pioneer 10's images of Ganymede and Callisto were still crude by modern standards, showing the moons as small disks with vague hints of lighter and darker regions. But for the first time, we were seeing these worlds as actual spheres rather than points of light. The images confirmed that both moons were indeed large, solid bodies with distinct surfaces. Pioneer 10's magnetometer also made measurements of the magnetic environment around Jupiter, though it wasn't close enough to the moons themselves to detect any intrinsic magnetic fields they might possess. Pioneer 11 followed a year later in December 1974 with a trajectory that brought it closer to some of the moons. The images improved, showing more clearly that Ganymede had distinct bright and dark regions on its surface, while Callisto appeared more uniformly dark and heavily cratered. These fleeting glimpses raised more questions than they answered, but they proved that close-up study of these moons was possible and that they had geological stories to tell. Then came Voyager. Voyager 1 arrived at Jupiter in March 1979, followed by Voyager 2 in July of the same year. These spacecraft carried far more sophisticated instruments than the pioneers, including much better cameras capable of resolving surface features in detail. The Voyager encounters with Jupiter's moons represented a revolution in our understanding, revealing worlds of complexity and beauty that no one had quite anticipated. Voyager 1's images of Ganymede showed a surface divided into two distinct types of terrain: dark, heavily cratered regions, apparently representing ancient surface, and brighter regions marked by complex patterns of grooves and ridges, suggesting more recent geological activity. The bright terrain showed evidence of tectonic processes, of the ice surface being pulled apart and restructured, creating vast systems of parallel grooves stretching for hundreds of kilometers. Here was a world that had experienced significant geological evolution. Not a simple frozen ball, but a tectonically active body with a complex history. Callisto presented a different picture. Voyager's images revealed it to be the most heavily cratered surface in the solar system, absolutely saturated with impact craters of all sizes. The surface appeared ancient, preserving a record of impacts stretching back billions of years to the early solar system, when debris from planetary formation was far more abundant. But Callisto also showed something extraordinary: enormous multi-ring impact structures called basins, the largest named Valhalla, spanning nearly 4,000 kilometers across. These ancient impact scars consisted of a relatively bright central region surrounded by concentric rings of ridges, like frozen ripples in ice, showing how the moon's surface responded to tremendous impacts billions of years ago. The Voyager encounters revealed that despite their similar sizes and compositions, Ganymede and Callisto had experienced very different geological histories. Ganymede showed evidence of internal activity, of heat that allowed its icy crust to deform and restructure itself over time. Callisto appeared geologically dead, its surface a pristine record of ancient impacts unmodified by later geological activity. Why should two similar-sized, similarly composed moons orbiting the same planet have such different evolutionary paths? This question would drive decades of subsequent research. Voyager's instruments also made other discoveries. They detected extremely thin atmospheres around both moons, far too tenuous to be breathable or even to significantly affect the surface conditions, but interesting scientifically as evidence of ongoing processes that could generate gas from the surface ices. The spacecraft measured more precise values for the moon's masses and sizes, refining the density calculations and confirming the mix of rock and ice in their interiors. The infrared instruments on Voyager detected temperature variations across the surfaces of both moons, showing how they cooled during Jupiter's long night and warmed during their day. These thermal measurements provided information about the surface materials, their ability to conduct and retain heat, suggesting that both moons were covered with a layer of fine-grained regolith, pulverized ice and rock created by billions of years of micrometeorite impacts. Perhaps most intriguingly, Voyager's magnetometer data hinted at magnetic anomalies near both Ganymede and Callisto, though the spacecraft didn't pass close enough to make definitive measurements. These hints suggested that there might be more to learn about these moons' magnetic properties, that perhaps they interacted with Jupiter's powerful magnetic field in ways that could reveal information about their interiors. The Voyager encounters transformed our understanding of the Galilean moons in just a few days of close approach, turning them from astronomical curiosities into real worlds with distinct personalities and histories. The images that came back, processed and enhanced, appeared on the front pages of newspapers and in science magazines, capturing public imagination. Here were alien landscapes as detailed and real as any we'd seen on the Moon or Mars, but fundamentally different, worlds of ice rather than rock, shaped by different processes under different conditions. But Voyager also revealed how much we didn't know. The spacecraft had time for only brief flybys, hours-long encounters that provided snapshots rather than sustained observation. Many questions remained unanswered. What caused the tectonic activity on Ganymede? Why was Callisto so different? Did these moons have subsurface oceans, like some scientists were beginning to suspect? What about those magnetic anomalies? Were they real? And if so, what did they mean? To answer these questions would require a different kind of mission, not a flyby, but an orbiter, a spacecraft that could take up residence in the Jovian system and study the moons repeatedly over months or years. That mission would eventually come, though it would take nearly 2 decades to design, build and launch it across the solar system to Jupiter. The Galileo spacecraft launched from the Space Shuttle Atlantis in October 1989, beginning a complex 6-year journey to Jupiter that would include gravity-assist flybys of Venus and Earth to build up the velocity needed to reach the outer solar system. The mission faced numerous challenges even before launch: budget constraints, technical issues, and the Challenger disaster that grounded the shuttle fleet for years and forced a change to a less powerful rocket, requiring the complex trajectory with multiple planetary flybys. When Galileo finally arrived at Jupiter in December 1995, it carried an orbiter designed to study the giant planet and its moons for at least 2 years, and a probe that plunged into Jupiter's atmosphere, returning data for nearly an hour as it descended before being crushed by the immense pressure. The orbiter's primary mission focused on Jupiter itself and the moon Io, whose volcanic activity made it a high-priority target. But the mission designers also planned multiple flybys of Europa, Ganymede and Callisto, using gravity assists from the moons to reshape the orbit and enable study of multiple targets. Between 1995 and 2003, when the spacecraft was deliberately crashed into Jupiter to avoid any risk of contaminating Europa with terrestrial microbes, Galileo completed 11 flybys of Europa, 8 of Ganymede, and 8 of Callisto. Each flyby brought the spacecraft within a few hundred or few thousand kilometers of a moon's surface, allowing detailed observations that revealed these worlds in unprecedented detail. For Ganymede, Galileo's observations transformed our understanding. The spacecraft's high-resolution camera mapped much of the surface at resolutions far better than Voyager had achieved, revealing the complexity of both the dark and bright terrain. The dark terrain proved to be heavily cratered, ancient surface perhaps 4 billion years old, similar in age to the lunar highlands on Earth's moon. But interspersed with this ancient surface were vast regions of bright terrain, marked by parallel grooves and ridges, showing where the surface had been pulled apart and restructured by tectonic forces. The grooved terrain told a story of internal heating at some point in Ganymede's past, enough to make the icy crust ductile enough to deform. Some grooved terrain appeared relatively old itself, showing impact craters that had formed after the grooves were created, suggesting that the tectonic activity had occurred long ago and then ceased. But other regions appeared younger, with fewer craters, hinting that some activity might have continued more recently in Ganymede's history. Galileo's instruments also studied Ganymede's composition in more detail. The near-infrared mapping spectrometer detected variations in ice composition across the surface, finding evidence not just for water ice, but also for other compounds mixed with it. Some regions showed signatures suggesting carbon dioxide ice or organic compounds, darkening agents that could explain the dark terrain. Other areas showed purer water ice, the bright frost of the grooved terrain. But perhaps Galileo's most astonishing discovery about Ganymede came from the magnetometer. During close flybys, the instrument detected clear evidence for an intrinsic magnetic field, a magnetic field generated within Ganymede itself rather than just induced by Jupiter's field. This discovery made Ganymede unique among moons, the only satellite in the solar system known to possess its own magnetosphere. The implications were profound. Magnetic fields are typically generated by dynamo processes, requiring liquid, electrically conducting material in motion, usually in a planet's core. Earth's magnetic field comes from convection in the liquid iron outer core. For Ganymede to have a magnetic field suggested that it too had a liquid conducting layer, most likely a liquid metallic or rock core kept molten by residual heat from formation and radioactive decay. The presence of this active core meant that Ganymede was far from geologically dead, that processes continued in its deep interior even if the surface appeared ancient and quiet. For Callisto, Galileo's observations confirmed and extended Voyager's findings. The surface was indeed saturated with craters, showing little evidence for internal geological activity. High-resolution images revealed craters of all sizes, from the giant multi-ring basins like Valhalla down to small fresh craters just a few kilometers across. The surface appeared to preserve a nearly complete record of impact history in the outer solar system, a record largely erased on more active worlds. But Galileo also found surprises at Callisto. The magnetometer data revealed that while Callisto didn't have an intrinsic magnetic field like Ganymede's, it did show a varying magnetic signature that changed depending on its position relative to Jupiter. This pattern suggested magnetic induction, Jupiter's rotating magnetic field inducing electric currents in some conducting layer within Callisto, which in turn created a secondary magnetic field. The most likely explanation for such a conducting layer was a subsurface ocean of liquid, salty water. This discovery astonished scientists. Callisto's surface showed no signs of geological activity, no evidence of the internal heating that would be needed to maintain a liquid ocean. Yet the magnetic data strongly suggested that such an ocean existed. How could this be? The leading explanation involved ammonia mixed with water, acting as an antifreeze that could keep water liquid at much lower temperatures. But this raised new questions. How much ammonia? How deep was the ocean? How had it persisted for billions of years in a moon that otherwise appeared geologically inactive? Galileo's gravity measurements, made by tracking tiny changes in the spacecraft's radio signal as it passed near the moons, provided information about internal structure. For Ganymede, the data indicated clear differentiation. The moon had separated into distinct layers, with denser rock in the center and less dense ice toward the surface, consistent with a moon that had been hot enough early in its history for materials to sort by density. For Callisto, the gravity data told a different story. The interior appeared less differentiated, perhaps never having been hot enough for complete separation of rock and ice. Over its 8 years in the Jovian system, Galileo built up a comprehensive picture of these two moons through repeated observations under different conditions. Each flyby added data, refined measurements, caught different surface regions in different lighting, built up coverage of regions missed in earlier passes. The patient accumulation of data across multiple encounters revealed complexities that no single flyby could have shown. The mission faced technical challenges throughout its lifetime. The high-gain antenna failed to fully deploy, severely limiting the data transmission rate and forcing mission controllers to develop sophisticated compression techniques and to carefully prioritize what data to send back. The spacecraft's trajectory through Jupiter's intense radiation environment gradually degraded its systems, requiring increasingly creative workarounds as components aged and failed. But despite these challenges, Galileo revolutionized our understanding of the Galilean moons, turning them from objects of speculation into real, complex worlds with individual histories. By the time Galileo ended its mission in 2003, diving into Jupiter's atmosphere to ensure it wouldn't accidentally crash into and contaminate Europa, it had provided enough data to keep scientists busy, analysing and interpreting for years afterward. The quiet giants had revealed themselves to be far more interesting than their calm surfaces suggested, hiding oceans and magnetic fields and complex histories beneath their ancient ice. Since Galileo's mission ended in 2003, our study of Ganymede and Callisto has continued through ground-based observations using increasingly sophisticated telescopes and through distant observations from spacecraft passing through the outer solar system. While we haven't had another dedicated mission to Jupiter's moons until very recently, these ongoing observations have continued to refine our understanding and occasionally revealed new surprises. The Hubble Space Telescope, operating above Earth's atmosphere and thus free from the blurring effects of air turbulence, has provided the highest resolution, ground-based images of the Galilean moons. Hubble observations have tracked changes in the moon's surfaces over time, looking for evidence of active geology, new impact craters, or other variations. While Ganymede and Callisto show far less dramatic change than Io, with its constantly erupting volcanoes, Hubble has documented subtle variations that help us understand ongoing processes. One of Hubble's most significant contributions came from ultraviolet spectroscopy of Ganymede. In the 1990s, even before Galileo's discoveries, Hubble detected oxygen emissions from Ganymede that indicated the presence of a very thin oxygen atmosphere, an exosphere, really, far too tenuous to breathe, but scientifically interesting. Later observations characterized this exosphere in more detail, showing how it varies with Ganymede's position in Jupiter's magnetosphere and helping to constrain models of how such an atmosphere is generated and maintained. Ground-based telescopes have also benefited from adaptive optics technology, which uses deformable mirrors to compensate for atmospheric turbulence in real time. Large telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile can now achieve resolution approaching what Hubble provides, allowing detailed spectroscopic studies of the Galilean moon surfaces from the ground. These observations have mapped the distribution of different ice types and contaminants across Ganymede and Callisto's surfaces, revealing regional variations that provide clues to their geological histories. Spectroscopic studies have detected carbon dioxide ice in certain regions on both moons, particularly on Callisto. The presence and distribution of CO2 provides information about surface chemistry, about how radiation from Jupiter processes the surface ices, creating new compounds and altering the original materials. Some of this CO2 might be primordial, incorporated when the moons formed, while other molecules might be created continuously by radiolysis, the breaking apart of water molecules by high-energy radiation and their subsequent recombination into new compounds. Infrared observations have characterized the thermal properties of the surfaces in detail, showing how quickly they heat up under sunlight and how much heat they retain. These measurements help us understand the nature of the surface material, the grain size of the regolith, and how compact or fluffy the surface ice might be. The thermal data also provides information about sublimation, the direct transformation of ice into water vapor, which contributes to the thin exospheres around both moons. In 2007, the New Horizons spacecraft, on its way to Pluto, passed through the Jovian system and used the gravity of Jupiter to accelerate toward its primary destination. During this flyby, New Horizons trained its instruments on the Galilean moons, including Ganymede and Callisto, providing another set of observations from a different perspective and with different instrument sensitivities than Galileo had carried. While New Horizons didn't approach as close as Galileo had, its observations complemented the earlier data and provided views of surface regions that Galileo had seen only at lower resolution. The Juno spacecraft, currently in orbit around Jupiter, studying the giant planet's interior structure, magnetic field, and atmospheric dynamics, occasionally observes the Galilean moons as well. While Juno's primary mission focuses on Jupiter itself, and its trajectory doesn't include close moon flybys, the spacecraft's instruments can study how Jupiter's magnetosphere interacts with the moons and can provide context for understanding the environment these moons exist within. Juno's measurements of Jupiter's magnetic field have refined our understanding of the magnetosphere that dominates the Galilean moon's environment. Jupiter's magnetic field is enormous, about 20,000 times stronger than Earth's, and extending millions of kilometers into space. The Galilean moons all orbit within this magnetosphere, subject to intense bombardment by charged particles trapped in Jupiter's magnetic field. Understanding this radiation environment is crucial for interpreting surface compositions and for planning any future missions that might visit these moons. Ground-based observations have also focused on the temporal variability of the moon's exospheres and surface properties. By observing them repeatedly over months and years, astronomers can detect seasonal changes, variations related to the moon's positions in their orbits, and longer-term trends that might indicate ongoing geological or chemical processes. These long-term monitoring campaigns complement the snapshot views provided by spacecraft missions. Radio observations using large arrays like the Very Large Array in New Mexico have detected thermal emissions from the Galilean moons, providing information about subsurface temperatures and thermal properties. These observations can penetrate slightly below the surface, revealing information about the temperature gradient in the upper layers of ice and helping to constrain models of heat flow from the interior. All of these ongoing observations from multiple facilities using multiple techniques continue to build our understanding of Ganymede and Callisto between dedicated spacecraft missions. Each observation adds a small piece to the puzzle, refining our knowledge, testing predictions from theoretical models, and occasionally revealing surprises that send scientists back to reconsider their assumptions. The picture that emerges from decades of observation is of two complex worlds that continue to be active in subtle ways despite their ancient surfaces. Both moons interact continuously with their environment, with Jupiter's magnetosphere, and with the rain of micrometeoroids that slowly gardens their surfaces. Both maintain thin exospheres through ongoing processes, and both, as we'll explore in more detail, harbour subsurface oceans that have persisted for billions of years through mechanisms we're still working to fully understand. As we await the next generation of missions to Jupiter's moons, these ongoing observations serve as a bridge, maintaining our connection to these distant worlds, ensuring that when those missions arrive, we'll have context for their findings and clear questions for them to address. The patient watch continues, telescopes on Earth and in space, keeping their eyes on the quiet giants, ready to catch any changes, any hints of ongoing activity, any clues to the deeper mysteries these worlds still hold. Among all the instruments that have studied Ganymede and Callisto, perhaps none have revealed more surprising secrets than the magnetometers, devices that measure magnetic fields with exquisite precision. These instruments, carried aboard both Voyager and Galileo spacecraft, detected magnetic signatures that told stories about processes occurring deep within these moons, processes invisible to cameras but fundamental to understanding their nature and evolution. A magnetometer works by measuring the strength and direction of magnetic fields in 3 dimensions, creating a vector that points from magnetic south to magnetic north. In the space environment around Jupiter, magnetometers must contend with the planet's enormous magnetic field, which dominates the entire region where the Galilean moons orbit. To detect a moon's own magnetic field, or magnetic signature, requires careful measurement during close approach, when the spacecraft is near enough that any moon-generated field becomes distinguishable from Jupiter's background field. When Voyager 1 passed by Ganymede in 1979, its magnetometer detected what seemed to be unusual perturbations in Jupiter's field near the Moon. The data hinted that something interesting was happening magnetically, but the flyby was too brief and the measurements too limited to draw firm conclusions. The tantalizing hints would have to wait for better data from a future mission. Galileo's magnetometer provided that better data. During the spacecraft's first close flyby of Ganymede on June 27, 1996, passing just 835 kilometers above the surface, the magnetometer recorded something extraordinary. A clear, distinct magnetic field originating from Ganymede itself, separate from and superimposed on Jupiter's field. The measurements showed that Ganymede possessed an intrinsic magnetic field, making it the only moon in the solar system known to generate its own magnetosphere. The implications took time to fully absorb. Planetary magnetic fields are typically generated by dynamo processes. Convection of electrically conducting fluids in a planet's interior, usually a molten iron core. Earth's magnetic field arises from convection in the liquid outer core, driven by heat escaping from the solid inner core and by chemical differentiation as iron crystallizes out. Mars once had a magnetic field generated by a similar process, but its core cooled and the dynamo ceased billions of years ago. For Ganymede to have an active magnetic field meant it must have a liquid, conducting, convecting region in its interior, given what we know about the moon's composition and density. The most likely explanation is a liquid iron or iron-sulfur core, kept molten by a combination of residual heat from Ganymede's formation and heat generated by the decay of radioactive elements like uranium, thorium and potassium in the rocky interior. The fact that this dynamo remains active today, more than 4.5 billion years after Ganymede formed, tells us something important about the moon's thermal evolution and internal structure. Subsequent Galileo flybys mapped Ganymede's magnetic field in more detail, revealing its structure and strength. The field is not particularly strong by planetary standards, about 1% of Earth's field strength at the surface, creating a magnetosphere that extends about 2 to 3 Ganymede radii from the surface, but it's strong enough to create a distinct magnetic bubble within Jupiter's much larger magnetosphere. A magnetosphere within a magnetosphere, a unique situation in the solar system. This magnetic bubble has consequences. Charged particles from Jupiter's magnetosphere, which would otherwise bombard Ganymede's surface directly, are deflected by the moon's own field, particularly near the magnetic poles. This creates regional differences in radiation exposure across Ganymede's surface, with equatorial regions receiving more particle bombardment than polar regions. These radiation differences affect surface chemistry, creating patterns in how the ice is processed and what compounds form. The interaction between Ganymede's magnetosphere and Jupiter's creates regions of complex magnetic topology. Field lines that connect between the two bodies, allowing particles to flow from one magnetosphere to the other. This interaction generates aurora on Ganymede, glowing emissions visible in ultraviolet light when Hubble observes the Moon. These aurora, like Earth's northern and southern lights, occur when charged particles follow magnetic field lines down into the upper atmosphere, exciting oxygen atoms that then emit characteristic wavelengths of light. Callisto's magnetic story proved different but equally intriguing. The magnetometer data from Callisto flybys showed no evidence for an intrinsic field like Ganymede's. If Callisto has a molten convecting core capable of generating a dynamo, that dynamo is either too weak to detect or not currently active. This difference between two similar-sized, similarly composed moons raises questions about their different thermal and structural evolution. But the magnetometer data from Callisto revealed something else: clear evidence for magnetic induction. As Callisto orbits through Jupiter's rotating magnetic field, that changing external field induces electric currents in any electrically conducting layers within Callisto. These induced currents, in turn, create a secondary magnetic field that the magnetometer could detect. The strength and pattern of this induced field depends on the electrical conductivity of the material carrying the currents. The most plausible explanation for a conducting layer within Callisto is a subsurface ocean of liquid, salty water. Pure water ice is a poor electrical conductor, and solid rock isn't much better under the cold conditions in Callisto's interior. But liquid water containing dissolved salts conducts electricity reasonably well, enough to carry the induced currents that create the observed magnetic signature. The characteristics of the induced field allow scientists to estimate the depth and extent of this conducting layer. Current models suggest Callisto's ocean lies roughly 100 to 200 kilometers beneath the surface, with a thickness that might exceed 100 kilometers. The ocean must contain enough dissolved salts to conduct electricity, perhaps similar to, or somewhat saltier than Earth's oceans. The presence of this ocean, existing within a moon that shows no surface evidence of internal heating or geological activity, presents a puzzle we're still working to fully solve. Ganymede's magnetometer data also hints at the possibility of a subsurface ocean, in addition to the moon's molten core. Some models suggest that the pattern of magnetic induction layered on top of the intrinsic field might indicate a conducting ocean layer within Ganymede's ice shell. If this interpretation is correct, Ganymede would possess both an active iron core generating an intrinsic field and a liquid water ocean generating an induced field, making its interior structure even more complex. The magnetometer discoveries transformed our understanding of these quiet giants. What appeared from their surfaces to be ancient geologically inactive worlds turned out to harbour active processes in their interiors, convecting liquid cores, hidden oceans, heat sources maintaining these liquid regions for billions of years. The magnetic data revealed hidden complexity, internal structure and activity, invisible to any camera or spectrometer, but clearly recorded in the precise, three-dimensional measurements of magnetic field strength and direction. These discoveries also raise new questions. What heat sources maintain Ganymede's liquid core? Why does Callisto have an ocean, despite apparent lack of geological activity? How do these oceans interact with the ice shells above them and the rocky mantles below? Are these oceans stable over billion-year timescales, or do they freeze and melt cyclically? Could they harbour conditions suitable for life, warm liquid water in contact with rock, perhaps with chemical energy sources available? The magnetometer, a relatively simple instrument measuring invisible fields, revealed some of the most profound secrets these moons hold. Secrets that will drive future exploration and shape our understanding of how moons evolve and what makes them habitable or inhospitable to life. The quiet giants had spoken, not through their visible surfaces but through their magnetic whispers, revealing hidden depths beneath ancient ice. Let's focus now on Ganymede in detail, beginning with the simple fact of its size. Ganymede measures 5,268 kilometers in diameter, making it not just the largest moon in the Jovian system, but the largest moon in the entire solar system. To put this in perspective, Ganymede is larger than the planet Mercury, which spans 4,879 kilometers across. It's more than twice the width of Pluto and substantially larger than Earth's moon, which measures 3,474 kilometers in diameter. With such substantial size comes substantial mass. Ganymede contains about 1.48 by 1023 kilograms of material, roughly twice the mass of Earth's moon. This mass creates surface gravity of about 1.43 meters per second squared, roughly 15% of Earth's gravity, enough to hold a thin atmosphere and enough to have shaped the moon's evolution significantly. If you could stand on Ganymede's surface, you'd weigh about 15% of your Earth weight, enough to keep your feet on the ground, but light enough that jumping would carry you several meters high with minimal effort. Despite its size and mass, Ganymede is not a planet. It orbits Jupiter rather than the Sun directly, making it by definition a satellite. But this classification seems almost arbitrary when considering Ganymede's physical characteristics. If Ganymede orbited the Sun independently, we'd surely call it a planet. Its size, its differentiated interior, its geological activity, its atmosphere and magnetosphere, all these characteristics are planetary in nature. Ganymede is a planet-class body that happens to orbit another planet rather than the Sun. The Moon orbits Jupiter at a distance of 1,400 kilometers, measured from center to center, or about 1,000 kilometers above Jupiter's cloud tops. This distance equals about 2.8 times the distance between Earth and our Moon, giving Ganymede substantial breathing room from Jupiter itself. The orbital period equals 7.15 Earth days, during which Ganymede completes one circuit around Jupiter at an average velocity of about 10.9 kilometers per second. Ganymede participates in what's known as a Laplace resonance with the inner Galilean moons, Io and Europa. For every one orbit Ganymede completes, Europa completes exactly 2 orbits, and Io completes exactly 4 orbits. This remarkable 1:4 ratio is not coincidental, but arises from gravitational interactions among the 3 moons over millions of years. The resonance has profound effects on all 3 moons' evolutions. For Io, the innermost of the 3, the resonance maintains its orbital eccentricity, preventing tidal forces from circularizing the orbit over time. This eccentric orbit causes tidal flexing as Io moves closer and farther from Jupiter, generating enormous heat through friction in the Moon's interior. This tidal heating makes Io the most volcanically active body in the solar system, with hundreds of active volcanoes continuously resurfacing the Moon. Europa also benefits from tidal heating due to the resonance, though less intensely than Io. This heating keeps Europa's subsurface ocean liquid and may drive geological activity that creates the young, fractured surface we observe. For Ganymede, the effects are more subtle. The Moon is far enough from Jupiter that tidal heating is less intense than for the inner moons, but the resonance still affects its orbital evolution and may contribute some heat to its interior. The resonance itself is stable and will likely persist for billions of years into the future. It represents a dynamical equilibrium, a configuration that the moons naturally settled into as they migrated and interacted gravitationally over the history of the Jovian system. Understanding this resonance helps us understand the system's formation and evolution, suggesting that the moons may have formed farther from Jupiter and migrated inward to their current positions, or that they formed in place but gravitational interactions adjusted their orbits into the resonant configuration. Ganymede's rotation is synchronously locked to its orbit, meaning it keeps the same face toward Jupiter at all times, just as Earth's moon does toward Earth. The rotation period equals the orbital period, 7.15 days. This synchronous rotation arises from tidal forces over millions of years. Jupiter's gravity raises tides in Ganymede's flexible body, creating a slight bulge oriented toward and away from Jupiter. If Ganymede rotated faster or slower than its orbital period, this bulge would be dragged out of alignment, creating a gravitational torque that speeds up or slows down the rotation until it matches the orbit. From Ganymede's surface, Jupiter would appear enormous, spanning about 19 degrees of sky, roughly 38 times the apparent diameter of our Moon as seen from Earth. But Jupiter would hang essentially motionless in the sky, always in the same position, never rising or setting, slowly going through its phases as Ganymede orbits, but never moving relative to the landscape. From Ganymede's far side, the hemisphere permanently facing away from Jupiter, the giant planet would never be visible at all, remaining forever below the horizon. The orbital characteristics and dynamical environment shape Ganymede's evolution in subtle ways. The Moon exists within Jupiter's magnetosphere, constantly bombarded by high-energy particles trapped in Jupiter's magnetic field. This radiation processes the surface ice, breaking apart molecules and allowing them to recombine into new compounds. The radiation exposure varies with Ganymede's position in its orbit, being more intense when the Moon passes through certain regions of the magnetosphere. Ganymede also experiences impacts from comets, asteroids, and smaller debris that have been gravitationally captured by Jupiter or that pass through the outer solar system. The impact rate is lower than in the inner solar system, where more debris remains from planetary formation, but over billions of years, impacts have thoroughly gardened Ganymede's surface, creating regolith and excavating material from depth. The largest impacts created multi-ring basins visible today, though erosion and subsequent geological activity have softened many ancient features. Understanding Ganymede as a complete world, with its size, mass, orbit, and dynamical environment, provides context for all the other characteristics we observe. Its surface features, its interior structure, its magnetic field, its thin atmosphere. This is not just a chunk of ice floating in space, but a complex, evolved world with a 4.5 billion year history, shaped by formation conditions, internal processes, external bombardment, and gravitational interactions with its siblings and with Jupiter itself. The quiet giant, patient in its orbit, holds all this history within its ancient ice, waiting for us to read the record and understand its story. When we look at images of Ganymede's surface, we immediately notice something striking. The Moon appears divided into two distinct types of terrain, as if someone drew a map with two different coloured pencils, dark and light, creating a patchwork across the entire globe. This dichotomy between dark and bright terrain tells the story of Ganymede's geological evolution, a tale of ancient surfaces preserved and younger regions reformed through tectonic activity. The dark terrain covers about 40% of Ganymede's surface, appearing in images as grey to brownish regions, heavily cratered and clearly ancient. These regions represent the original crust of Ganymede, material that has remained relatively unchanged for perhaps 4 billion years, preserving a record of the early solar system when impact rates were much higher than today. The crater density in dark terrain approaches saturation, meaning that new impacts generally destroy or obscure older craters rather than adding to the total count, indicating extreme age. The craters themselves show various stages of degradation. Some remain relatively fresh with sharp rims and visible ejecta blankets, while others appear subdued, their features softened by subsequent impacts, by radiation processing of the surface, or by slow, viscous relaxation of the ice over billions of years. This range of preservation states allows scientists to untangle the relative ages of different features and to understand how Ganymede's surface evolves over time. Interspersed with the dark terrain are vast regions of bright terrain, covering about 60% of the surface, appearing lighter in images due to fresher, cleaner ice exposed at the surface. But it's not just the brightness that distinguishes these regions, but their distinctive textures. Complex systems of parallel grooves and ridges, running for hundreds or even thousands of kilometers, creating patterns that suggest tectonic processes have pulled the crust apart and restructured it. These grooved terrain regions, called sulci in geological terminology, show a variety of forms. Some consist of parallel ridges and troughs just a few hundred meters high and a kilometer or two apart, creating a corrugated appearance like a washboard carved in ice. Other regions show broader, more complex patterns with multiple intersecting sets of grooves, suggesting multiple episodes of deformation from different directions. Still, other areas show less regular patterns, swirls and patches of disrupted terrain where the surface has been thoroughly reworked. The grooves form through extension, through the ice crust being pulled apart. As this happened, fresher ice from below was exposed or erupted onto the surface, creating the brighter appearance. The parallel nature of many groove systems suggests that the extension happened in a coordinated way, perhaps driven by convection in the ice shell below, or by tidal forces creating stress patterns in the crust. The age relationships between dark and bright terrain are clear. The grooved terrain is younger, cutting across and disrupting the older, dark cratered terrain. We can see this in countless examples where groove systems truncate craters, or where dark terrain survives as isolated patches surrounded by younger grooved regions. But even the bright terrain isn't uniformly young. Some grooved regions show numerous impact craters, indicating they formed relatively long ago and have been exposed to impacts for billions of years. Other regions show fewer craters, suggesting more recent formation. This suggests that the tectonic activity that created the grooved terrain wasn't a single episode, but occurred multiple times over Ganymede's history, perhaps extending over billions of years. Different regions of grooved terrain formed at different times, creating the complex patchwork we observe today. The driving force for this activity remains debated. Tidal heating from the orbital resonance with Io and Europa may contribute, though Ganymede's distance from Jupiter means it experiences less tidal flexing than its inner neighbours. Another possibility involves differentiation and internal evolution. As Ganymede's interior separated into layers, with denser materials sinking and lighter materials rising, the process may have driven expansion of the outer layers, cracking the crust and allowing newer material to surface. Computer models suggest that complete differentiation could have increased Ganymede's radius by several percent, enough to create extensive tectonic features at the surface. Some scientists have suggested that the tectonic activity might relate to the formation of Ganymede's magnetic field. If convection began in a liquid iron core, the associated reorganization of the interior might have transmitted stress to the outer layers, driving surface tectonics. This would link the grooved terrain formation to the onset of the dynamo that generates Ganymede's magnetosphere, though the exact timing and causal relationships remain uncertain. The boundary between dark and bright terrain often shows complex relationships, with fingers of one terrain type extending into the other, suggesting that the processes creating the grooved terrain didn't simply replace dark terrain wholesale, but worked gradually, breaking up the ancient surface piece by piece and forming newer terrain in the gaps. Some regions show what appear to be remnants of dark terrain within grooved areas, isolated patches that survived the tectonic disruption, like ancient islands in a sea of newer surface. High-resolution images from Galileo revealed additional complexities in both terrain types. The dark terrain isn't uniformly dark, but shows subtle variations in brightness and texture, perhaps indicating different ages or different compositions. Some dark regions appear slightly brighter or less heavily cratered than others, suggesting they might be somewhat younger or that they have experienced different degrees of surface processing. The grooved terrain also shows variety. Some sulci have very regular, straight parallel grooves, while others meander or curve following patterns that might reflect the local stress field when they formed or the properties of the ice shell at different locations or times. The spacing and amplitude of grooves varies from region to region, perhaps indicating different formation mechanisms or conditions. Ganymede's surface also shows evidence for other geological processes. Some regions display what appear to be ancient impact basins, large circular structures hundreds of kilometers across, now so degraded by subsequent geological activity that they're barely recognizable. These ghost basins suggest that Ganymede experienced large impacts early in its history, before the grooved terrain formed and obscured or modified the impact structures. There's also evidence for cryovolcanism, though far more subtle than the active volcanism on Io, or even the possible recent activity on Europa. Some regions of bright terrain may have been resurfaced by eruptions of liquid water or water ice slurries from the interior, flooding older terrain and creating smoother surfaces. The evidence is circumstantial, inferred from morphology and crater density rather than from direct observation of volcanic features, but it's consistent with models suggesting that a young Ganymede with a warmer interior might have experienced ice volcanism. As your breathing slows and your thoughts begin to drift towards sleep, imagine standing at the boundary between dark and bright terrain on Ganymede's surface, 1 foot on ancient cratered ice that has remained unchanged for 4 billion years, the other on grooved terrain perhaps only 1 or 2 billion years old. Behind you stretches a landscape pockmarked with countless impacts, a frozen record of solar system history. Before you, parallel ridges and troughs march toward the horizon, testament to forces that pulled the crust apart and renewed the surface. Above, Jupiter dominates the sky, its presence a constant reminder that you stand on a moon, a world shaped not just by its own internal evolution, but by gravitational forces linking it to its siblings and to the massive planet it circles endlessly. Among all the remarkable characteristics that make Ganymede unique, perhaps none is more scientifically profound than its intrinsic magnetic field and the magnetosphere that field creates. This discovery, made by the Galileo spacecraft's magnetometer during its first close flyby in 1996, elevated Ganymede from an interesting moon to a truly exceptional world, the only satellite in our solar system known to generate its own magnetic field from an internal dynamo. To understand why this is so significant, we need to understand how planetary magnetic fields work. Earth's magnetic field arises from convection in the liquid iron outer core. The Earth's core consists of a solid inner sphere of iron, about 1,020 kilometers in radius, surrounded by a liquid outer core of iron mixed with lighter elements like sulfur and oxygen, extending to about 3,480 kilometers from Earth's center. Heat escaping from the solid inner core, combined with compositional convection as iron crystallizes out and lighter elements rise, drives fluid motion in the outer core. This moving, electrically conducting fluid acts as a dynamo, converting kinetic energy of motion into magnetic energy. The process is complex, involving feedback loops where existing magnetic fields influence the fluid flow, which in turn modifies the magnetic field, creating a self-sustaining system. The result is Earth's dipole magnetic field, oriented roughly north-south, extending far into space and creating the magnetosphere that shields our planet from solar wind and cosmic radiation. For Ganymede to possess an intrinsic magnetic field requires similar conditions: a liquid electrically conducting region undergoing convective motion driven by some heat source. Given Ganymede's size, composition and density, models suggest this conducting region is most likely a liquid iron or iron-sulfur core at the moon's center. The core probably measures between 500 and 900 kilometers in radius, roughly 20 to 30% of Ganymede's total radius, containing a significant fraction of the moon's mass. The heat driving convection in this core comes from two primary sources. First, residual heat from Ganymede's formation remains stored in the interior. When Ganymede accreted from the solar nebula 4.5 billion years ago, the impacts of infalling material converted kinetic energy to heat, warming the growing moon. For a body as large as Ganymede, this primordial heat can persist for billions of years, slowly leaking out through the surrounding layers. Second, radioactive decay of unstable isotopes in the rocky mantle surrounding the core generates heat continuously. Elements like uranium-238, thorium-232, and potassium-40 have half-lives of billions of years and produce heat as they decay into stable daughter products. While the heat production rate per kilogram is tiny, the large mass of Ganymede's rocky interior means the total heat production is substantial, enough to maintain a liquid core and drive convection over geological timescales. The magnetic field strength at Ganymede's surface measures about 750 nanotesla near the equator, roughly 1.3% of Earth's surface field strength. While weak compared to Earth, it's strong enough to create a distinct magnetosphere, a region of space dominated by Ganymede's field rather than Jupiter's. This magnetosphere extends about 2 to 3 Ganymede radii from the surface, creating a protective bubble within Jupiter's much larger magnetosphere. This magnetosphere within a magnetosphere creates a unique situation. Charged particles flowing in Jupiter's magnetospheric plasma encounter Ganymede's magnetic field and must flow around it, creating bow shocks and magnetospheric boundaries similar to those around planets. Ganymede's field lines close around the Moon, with field lines emerging from the magnetic South Pole, looping through space and re-entering at the magnetic North Pole. The interaction is not static but highly dynamic. Jupiter's magnetosphere rotates with the planet's 10-hour period, creating a flow of magnetospheric plasma past Ganymede, which orbits Jupiter every 7.15 days. From Ganymede's perspective, Jupiter's rotating magnetic field and plasma flow past the Moon at about 140 kilometers per second. Ganymede's magnetosphere must constantly withstand this supersonic flow, creating complex plasma physics phenomena at the boundaries. The magnetic field lines of Ganymede and Jupiter can connect, creating regions of open field lines that link the two magnetospheres. Charged particles can flow along these connected field lines, creating electrical currents between Jupiter and Ganymede, similar to the Io plasma torus that links Io to Jupiter. These currents deposit energy in Ganymede's polar regions, creating aurora, glowing oxygen emissions visible in ultraviolet light when space telescopes observe the Moon. Hubble observations detected these aurora in the late 1990s, revealing bright spots at Ganymede's magnetic poles, where particles spiral down field lines into the thin atmosphere, exciting oxygen atoms that emit characteristic ultraviolet wavelengths. The aurora's position and brightness vary depending on Ganymede's position in Jupiter's magnetosphere and on the orientation of Ganymede's magnetic field relative to Jupiter's, creating a complex, time-variable phenomenon that scientists use to study both magnetospheres. The magnetic field also affects surface processes. In regions where Ganymede's field is strong, particularly near the magnetic poles, charged particles from Jupiter's magnetosphere are deflected or at least partially shielded from reaching the surface. At the magnetic equator, where the field lines run parallel to the surface rather than plunging vertically, there's less protection, and Jupiter's particles can more easily reach the surface. This creates a pattern of differential radiation processing across Ganymede's surface. Spectroscopic observations have detected this pattern, showing differences in ice composition and brightness that correlate with the magnetic field structure. Regions near the magnetic poles, where particles are deflected, show different concentrations of certain compounds compared to equatorial regions. This magnetic control on surface chemistry provides a direct link between Ganymede's deep interior, where the field is generated, and its surface, where we observe the effects. The existence of an active magnetic field also tells us that Ganymede remains thermally active in its interior, that it hasn't completely cooled and solidified like some smaller bodies have. The Moon maintains sufficient heat flux from core to surface to drive the convection necessary for dynamo action. This has implications for other aspects of Ganymede's evolution, suggesting that the interior may be partially molten or at least hot enough for solid-state convection, which could drive the tectonic processes that created the grooved terrain. Some models suggest that Ganymede's magnetic field might not have been continuous over its entire history. The dynamo might have started, stopped, and restarted multiple times as the thermal and compositional state of the core evolved. If the field did shut off temporarily, That would have exposed Ganymede's entire surface to intense radiation during those periods, potentially leaving signatures in surface chemistry or in the nature of the regolith. Looking for such signatures could help constrain the history of the magnetic field. The discovery of Ganymede's magnetic field raises questions about other large moons. Why doesn't Callisto, similar in size and composition, have an intrinsic field? What about Titan, Saturn's largest moon, comparable in size to Ganymede? So far, no other moon has shown evidence for an active dynamo. Understanding what makes Ganymede special, what combination of size, composition, thermal evolution, and perhaps tidal heating or orbital resonance effects allowed it alone to maintain an active core dynamo, remains an open question, driving theoretical work and awaiting data from future missions. As we continue to study Ganymede's magnetic field and magnetosphere, measuring how they vary with time, how they respond to changes in Jupiter's magnetosphere, how they affect and are affected by the Moon's ionosphere and exosphere, we're learning not just about this particular moon, but about fundamental magnetospheric physics and about the requirements for dynamo action in planetary bodies. The quiet giant speaks to us through its magnetic field, revealing secrets about its deep interior, its thermal evolution, and the complex physical processes that make this moon uniquely among all satellites a magnetized world. Beneath Ganymede's ancient cratered surface, beneath the bright grooved terrain and the dark impact-scarred regions, beneath kilometers of solid ice, lies something that would have seemed impossible just a few decades ago. A global ocean of liquid water, hidden in darkness, maintained for billions of years, despite the moon's great distance from the sun. The evidence for this ocean comes from multiple sources, converging to paint a compelling picture. The magnetic induction signal detected by Galileo's magnetometer provides perhaps the strongest evidence. When Jupiter's rotating magnetic field sweeps past Ganymede, it should induce electric currents in any electrically conducting layers within the moon. The strength and pattern of the induced magnetic field that Galileo measured suggests the presence of a global conducting layer, most plausibly a salty ocean, lying beneath the surface. The depth of this ocean can be estimated from several lines of evidence. Models of Ganymede's interior structure, constrained by the moon's mass, density, and moment of inertia, suggest that the ocean lies roughly 150 to 200 kilometers beneath the surface. The ice shell above the ocean consists of multiple layers with different properties, determined by the temperature and pressure at different depths. Near the surface, where temperatures are coldest, the ice exists as ordinary ice 1, the familiar form of ice we experience on Earth. But deeper down, as pressure increases, ice transforms into denser, crystalline phases. At pressures corresponding to depths of perhaps 100 kilometers or more, ice 1 gives way to high-pressure ice polymorphs, like ice 3, ice 5, or ice 6, which have different crystal structures and higher densities. These high-pressure ices can exist at higher temperatures than ice 1, creating an insulating layer between the frigid surface and the warmer ocean below. The ocean itself likely sits between this high-pressure ice shell and an underlying rocky mantle. Current estimates suggest the ocean might be 100 kilometers thick or more, a vast reservoir of liquid water exceeding the volume of all Earth's oceans combined. The water would be cold by terrestrial standards, probably just a few degrees above the freezing point, but definitely liquid, kept from freezing by heat rising from Ganymede's rocky interior and possibly by salts dissolved in the water that lower the freezing point. The salinity of Ganymede's ocean remains uncertain, but is probably significant. The magnetic induction measurements require the ocean to conduct electricity, which pure water does poorly. Dissolved salts, particularly sulfates or chlorides, leached from rocks in contact with the ocean's base, would provide the necessary conductivity. The salt concentration might be similar to Earth's oceans, or possibly higher, creating a brine that conducts electricity readily and has an even lower freezing point than pure water. At the base of the ocean, liquid water contacts the rocky mantle, creating conditions that interest astrobiologists. On Earth, the interface between water and rock provides opportunities for chemistry, for minerals to dissolve and react, for chemical energy to become available to support life. Hydrothermal systems on Earth's ocean floor support thriving ecosystems based not on sunlight, but on chemical energy extracted from reactions between hot water and rock. Could similar processes occur in Ganymede's dark ocean? The heat sources maintaining the ocean include radioactive decay in the rocky mantle and residual heat from formation. Tidal heating may contribute as well, though Ganymede's distance from Jupiter and the mechanics of the Laplace resonance mean tidal effects are much weaker than for Io or Europa. Still, even modest tidal heating, sustained over billions of years, could provide significant energy to the interior, helping to maintain the ocean and possibly driving convection in both the ice shell and the rocky mantle. The ocean's stability over geological time presents interesting questions. Has the ocean existed continuously since Ganymede formed, or has it frozen and melted cyclically as the moon's internal heat production has varied? If Ganymede was hotter early in its history, with more vigorous radioactive heating and more residual formation heat, the ocean might have been warmer and perhaps thicker. As the interior has cooled over billions of years, the ocean might have thinned somewhat, with ice thickening from both above and below as heat flow declined. But the ocean likely remains today, sustained by ongoing heat production and possibly stabilized by the insulating effect of the high-pressure ice layer. Unlike Europa, where the thin ice shell might crack and allow ocean water to reach the surface occasionally, Ganymede's thick shell probably isolates the ocean completely from the surface. No direct connection exists between the hidden ocean and the vacuum of space, meaning the ocean remains a closed system, evolving chemically and physically over billions of years without exchange with the exterior. This isolation has implications for habitability. On one hand, the ocean is protected from radiation that bombards the surface, creating a stable environment where conditions could remain relatively constant for geological periods. On the other hand, the lack of connection to the surface means no fresh chemicals or organic materials from space can easily reach the ocean, limiting the potential for complex chemistry. Life, if it exists in Ganymede's ocean, would need to survive on whatever chemical energy is available from water-rock interactions and on whatever organic materials were incorporated when the moon formed. The presence of an ocean also affects Ganymede's geological evolution. Liquid water is far more mobile than ice, allowing heat to be transported by convection rather than just conduction. The ocean acts as a thermal boundary layer, efficiently moving heat from the rocky interior to the overlying ice shell. This heat transport affects how the ice shell behaves, how quickly it cools, and how it responds to stresses, potentially influencing the formation of the grooved terrain we observe at the surface. Some models suggest that the ice shell itself might undergo convection, with warmer ice rising from depth and cooler ice sinking from the surface, slowly overturning over millions of years. If the ice shell convects, it could help explain the tectonic activity that created the bright terrain. Convection cells in the ice might create surface expressions as divergent boundaries where upwelling occurs and convergent boundaries where downwelling happens, similar to plate tectonics on Earth, but with ice instead of rock. The temperature structure of the ice shell matters for understanding its mechanical behavior. Near the surface, where temperatures are extremely cold, around 100 Kelvin at the equator, and even colder near the poles, ice behaves as a brittle solid that fractures rather than flows when stressed. But deeper in the shell, where temperatures approach the melting point, ice becomes ductile, flowing slowly in response to stress like a very viscous fluid. This transition from brittle to ductile behavior occurs at a depth determined by the temperature gradient, perhaps 10 to 20 kilometers down. This brittle ductile transition zone may control how features form at the surface. Fractures and grooves can propagate through the brittle upper layer, but when they reach the ductile zone, further extension is accommodated by flow rather than fracturing. This could explain why grooves have characteristic depths and widths, rather than extending arbitrarily deep into the crust. As you drift deeper towards sleep, imagine descending through Ganymede's layers. First through the heavily cratered surface ice, past impact scars billions of years old, through the brittle upper shell where fractures and grooves mark ancient tectonic activity, deeper into the ductile ice slowly convecting over geological time. Through the transition to high-pressure ice phases you'd never encounter on Earth, and finally into the ocean itself, a vast, dark, cold sea beneath hundreds of kilometers of ice, where water has flowed in silence for billions of years, touching rocks at the bottom, kept liquid by the gentle warmth of a moon that refuses to completely cool, a hidden sea larger than all Earth's oceans, waiting in patient darkness beneath the quiet giant's frozen face. To understand Ganymede, we must understand ice, not just the familiar substance that forms in winter or floats in our drinks, but ice in all its complexity, its multiple crystalline phases, its ability to flow like rock over geological time, its response to pressure and temperature and stress, and how it behaves at the extreme conditions in a planetary body orbiting Jupiter more than 5 astronomical units from the Sun. Water ice can exist in at least 18 different crystalline phases, each stable under different conditions of temperature and pressure. The ice we encounter in everyday life, floating in lakes or coating trees in winter, is Ice 1H, the hexagonal phase stable at low pressures and temperatures below 273 Kelvin at Earth's atmospheric pressure. This ice has a relatively open crystal structure, which is why it's less dense than liquid water, why ice floats, a property with profound implications for life on Earth, but also for understanding icy worlds. At higher pressures, water molecules can pack more efficiently, creating denser ice phases. Ice 3 forms at pressures around 300 megapascals and temperatures around 250 Kelvin, conditions that would exist perhaps 100 kilometers deep in Ganymede's ice shell. Ice 5 and Ice 6 form at still higher pressures, potentially present at depths approaching 200 kilometers. Each phase has a distinct crystal structure, distinct density, and distinct mechanical and thermal properties. These phase transitions matter for Ganymede's structure and evolution. As ice transforms from one phase to another, with depth its density increases, which affects how efficiently the shell can transmit pressure and support topography. The phase transitions also affect thermal conductivity, how readily heat can flow through the ice from the interior to the surface. Ice 6, for instance, conducts heat more efficiently than Ice 1H, which affects the temperature gradient in the deep ice shell. But perhaps most importantly for Ganymede's geology, ice's mechanical properties change dramatically with temperature and pressure. At the cold surface temperatures, around 100 to 150 Kelvin, ice behaves as a brittle solid, fracturing when stressed beyond its strength. This brittle behavior allows impact craters to form and persist, allows grooves and fractures to develop as the crust is stressed by tectonic forces, and allows topography to be supported over billions of years. Deeper in the ice shell, where temperatures approach the melting point, ice undergoes a transition to ductile behavior, flowing slowly in response to stress through a process called creep. Ice creep occurs through several mechanisms. Individual water molecules can migrate through the crystal lattice, allowing the ice to deform without fracturing. Entire crystal grains can slide past each other along grain boundaries, and under sufficient stress the ice can actually recrystallize, with old grains being consumed and new grains forming in less stressed orientations. The creep rate depends strongly on temperature, roughly doubling for every 10 Kelvin increase near the melting point. This temperature sensitivity means that even small temperature differences can create large differences in ice viscosity and deformation rate. Ice at 250 Kelvin might be effectively rigid on geological timescales, while ice at 270 Kelvin flows readily, and ice very near the melting point at 273 Kelvin can flow almost like a fluid. This temperature-dependent rheology controls how Ganymede's ice shell responds to stresses. The cold, brittle surface layer can support topography and maintain sharp features like crater rims and groove walls, but the warm, ductile, deeper layer flows over millions of years, slowly relaxing topography and allowing the shell to deform in response to tidal stresses or to convective motions in the ice itself. The concept of ice convection deserves attention. Like the rock mantle of Earth, which convects to transport heat from the core to the surface, driving plate tectonics in the process, Ganymede's ice shell might convect if it's thick enough and if the temperature difference between top and bottom is large enough. Warm ice near the base of the shell, heated by the underlying ocean or by tidal dissipation, would be less dense than cold ice near the surface. This density inversion creates instability. Warm ice wants to rise, cold ice wants to sink. Whether convection actually occurs depends on a dimensionless parameter called the Rayleigh number, which compares the driving forces for convection, thermal expansion and gravity, to the resisting forces, viscosity and thermal diffusion. Calculations suggest that Ganymede's ice shell might be in a regime where convection is possible, at least in the lower, warmer portions of the shell. If so, this convection could manifest at the surface as regions of extension, where warm ice rises, and regions of compression, where cold ice sinks, potentially creating or contributing to the grooved terrain. Ice on Ganymede's surface also undergoes modification through radiation processing. Jupiter's magnetosphere bathes Ganymede in energetic charged particles, electrons, protons, and heavier ions accelerated to high velocities by Jupiter's magnetic field. When these particles strike the ice, they break apart water molecules through radiolysis, creating free hydrogen atoms, oxygen atoms, and molecular fragments like hydroxyl OH. Some of these fragments recombine to form water again, but others react to form new compounds. Oxygen molecules, O2, can form and become trapped in the ice or escape to form Ganymede's tenuous exosphere. Hydrogen peroxide, H2O2, forms through reactions between oxygen atoms and is detected spectroscopically on Ganymede's surface. Other compounds form if carbon or sulfur is present, perhaps delivered by cometary impacts, creating a complex mixture of species. This radiation chemistry darkens the ice over time, creating defects in the crystal structure that absorb light and giving old irradiated surfaces a darker appearance. This helps explain why Ganymede's ancient dark terrain is darker than the younger bright terrain. The dark regions have been exposed to radiation for billions of years, accumulating damage and darkening agents, while the bright regions were resurfaced more recently and haven't yet accumulated as much radiation damage. The darkening isn't uniform across the surface. Ganymede's magnetic field, as we discussed, shields some regions from charged particles while leaving others more exposed. The regions near the magnetic poles, where field lines plunge vertically into the Moon, are relatively protected, while equatorial regions receive more intense bombardment. Spectroscopic mapping reveals patterns in surface composition that correlate with this magnetic shielding, providing direct evidence that the magnetic field affects surface processes. Temperature variations across Ganymede's surface also affect the ice. Near the equator, surface temperatures reach about 150 Kelvin during the day, while near the poles temperatures barely exceed 100 Kelvin even in full sunlight. These temperature differences affect how the ice responds to radiation, how rapidly molecules can migrate and react, and how efficiently volatile compounds can be retained or lost to space. Sublimation, the direct transformation of ice to water vapor without passing through a liquid phase, occurs continuously across Ganymede's surface. The rate is slow, limited by the cold temperatures, but over billions of years, sublimation has removed substantial amounts of ice from the surface. This loss is preferential. Water ice sublimes more readily than some contaminants, so sublimation can concentrate non-water compounds at the surface, contributing to darkening and altering the surface composition over time. The ice on Ganymede has also been pulverized by micrometeorite impacts over billions of years. These tiny impacts, too small to create visible craters, gradually break surface ice into finer and finer particles, creating a regolith layer of loose, fragmented material tens of meters or more thick. This regolith affects how the surface reflects light, how it retains heat, and how it responds to larger impacts. When a large impactor strikes, it excavates not just solid ice, but this fragmented regolith, mixing materials from different depths and creating the complex crater morphologies we observe. Understanding ice physics at Ganymede requires integrating knowledge from multiple fields: crystal structure and phase transitions from solid-state physics, rheology and convection from geophysics, radiation chemistry from planetary science, and thermal evolution models that tie everything together. The ice isn't just frozen water, but a complex evolving system responding to temperature, pressure, stress, radiation, and impacts shaped over billions of years into the structure we observe today. The quiet giant's face, patient and ancient, tells stories written in ice physics, in phase transitions and creep rates and radiation damage, stories we're learning to read through careful observation and theoretical modelling. In the cold vacuum of space, where Ganymede orbits Jupiter at a distance that receives only 4% of the sunlight that warms Earth, you might expect the Moon's surface to be exposed directly to the emptiness of space, with no atmosphere at all to mediate between ice and void. But Ganymede does possess an atmosphere, though calling it that stretches the word to its limits. This is an exosphere, so tenuous that its particles almost never collide with each other, so thin that it would count as a perfect vacuum by laboratory standards, yet substantial enough to detect and study, revealing processes that continuously modify Ganymede's surface and creating phenomena like aurora at the magnetic poles. The primary constituent of Ganymede's exosphere is molecular oxygen, O2, along with some atomic oxygen, O. The total atmospheric pressure at the surface amounts to roughly 1 microbar, about 1/1,000,000th of Earth's sea level atmospheric pressure, or roughly equivalent to the pressure in the best vacuum chambers we can create on Earth. At this pressure, the mean free path, the average distance a molecule travels between collisions, exceeds hundreds of kilometers, far larger than Ganymede's radius. Molecules don't collide with each other, but instead follow ballistic trajectories, arcing up from the surface and falling back down elsewhere or escaping to space entirely. The oxygen in Ganymede's exosphere comes primarily from radiolysis of surface ice. When charged particles from Jupiter's magnetosphere strike water ice molecules at the surface, they break apart the H2O molecules, liberating oxygen atoms and hydrogen atoms. The hydrogen, being very light, escapes to space quickly, while the oxygen can recombine to form O2 or remain as atomic oxygen. Some of this oxygen becomes trapped in the ice, but some escapes into the exosphere, creating a continuous supply that maintains the thin atmosphere against losses to space. The exosphere's density varies across Ganymede's surface, controlled by several factors. Temperature affects the rate of sublimation and the rate at which oxygen can escape from the ice. The surface is warmer at the equator than at the poles, leading to higher exospheric densities at lower latitudes. The magnetic field affects the rate of radiolysis, with regions receiving more intense radiation, producing more oxygen. And the surface composition matters. Regions with fresher, purer ice might produce oxygen more efficiently than heavily processed, darkened regions where oxygen has already been depleted from the upper layers. The exosphere also varies with Ganymede's position in its orbit around Jupiter. When Ganymede passes through different regions of Jupiter's magnetosphere, the intensity and energy of bombarding particles change, altering the rate of radiolysis and thus the rate of oxygen production. When Ganymede is downstream in the magnetosphere, sheltered somewhat by Jupiter itself, radiation exposure decreases, and so does exospheric oxygen production. When Ganymede is upstream, fully exposed to the magnetospheric flow, production increases. Observations with the Hubble Space Telescope have detected these variations, measuring the strength of oxygen emissions in ultraviolet light as Ganymede orbits Jupiter. The emissions are strongest near local noon, where the sun-warmed surface releases oxygen most readily, and weaker near the terminator and on the night side. The emissions also show the effects of magnetic shielding, with patterns that match the structure of Ganymede's magnetic field, providing another confirmation that the field affects surface processes. Besides oxygen, Ganymede's exosphere contains trace amounts of other species. Atomic hydrogen, though it escapes quickly, is continuously produced by radiolysis and exists in small concentrations. Water vapor, subliming from the surface, contributes molecules that quickly photodissociate, break apart under solar ultraviolet light, contributing to the hydrogen and oxygen populations. And impacts by micrometeoroids vaporize small amounts of ice, temporarily creating local enhancements in exospheric density. The presence of an oxygen exosphere around an icy moon might seem surprising, but it's actually common among the large satellites of the outer solar system. Europa also has an oxygen exosphere produced by similar processes. Saturn's moons Rhea and Dione show evidence for thin oxygen atmospheres. Even tiny icy bodies can have exospheres if they're exposed to sufficient radiation. The phenomenon teaches us about the physics of how surfaces respond to energetic particles and how stable atmospheres can be maintained even in the absence of geological activity. For Ganymede, the exosphere has implications beyond atmospheric science. It represents mass loss from the surface, ice molecules being broken apart, and their components either lost to space or incorporated into the magnetosphere. Over billions of years, this process has removed substantial amounts of surface ice, perhaps meters or tens of meters of material, enough to affect the surface's appearance and composition. The preferential loss of hydrogen means the surface has become enriched in oxygen-containing compounds relative to pure water ice, contributing to the compositional complexity we detect spectroscopically. The exosphere also affects how we might explore Ganymede with spacecraft. Any future lander or rover would operate in this near-perfect vacuum, requiring systems designed to handle the lack of any atmospheric pressure. There would be no wind, no weather, no atmospheric sounds, but there would be a constant invisible rain of oxygen molecules, occasionally impacting the spacecraft surfaces, and a constant bombardment of energetic particles from Jupiter's magnetosphere, which would need to be accounted for in mission design. The aurora, visible in Hubble images as bright spots in ultraviolet light at Ganymede's magnetic poles, result from interactions between the magnetosphere and the exosphere. Charged particles spiraling down along magnetic field lines collide with oxygen atoms in the exosphere, exciting them to higher energy states. When the excited atoms relax back to their ground state, they emit characteristic wavelengths of ultraviolet light, creating the glow we detect. The aurora's position shifts as Ganymede's magnetic field orientation changes relative to Jupiter's, and its brightness varies with the intensity of particle precipitation. These aurora are far fainter than Earth's northern and southern lights, requiring sensitive space telescopes to detect. But they serve similar scientific purposes, acting as visible tracers of invisible magnetospheric processes. By studying when and where the aurora appear, how bright they become, and how they vary with time, scientists can infer properties of both the magnetosphere and the exosphere, probing regions and phenomena that can't be studied any other way. The thin exosphere, invisible to human eyes, unbreathable, and barely substantial enough to measure, nevertheless tells important stories about Ganymede. It reveals the ongoing modification of the surface by radiation, the loss of material to space, the interaction between the magnetic field and Jupiter's magnetosphere, and the processes that have shaped this moon over billions of years. The atmosphere, thin as a whisper, speaks volumes to those who know how to listen, adding another layer of complexity to the quiet giant, another aspect of the hidden activity occurring constantly beneath and around the ancient, seemingly unchanging surface. As your consciousness begins to drift and soften, imagine standing on Ganymede's surface, the near-perfect vacuum around you, a handful of oxygen molecules per cubic centimetre dancing invisibly in the space around you, each one liberated from the ice by a charged particle from Jupiter, each one contributing to the faint glow of aurora at the poles, the quiet breathing of a world whose atmosphere is more absence than presence, but presence nonetheless. If Ganymede's surface tells a story of geological renewal and tectonic activity, punctuating ancient terrain, Callisto's surface tells a different story entirely, a story of preservation, of an ancient face barely modified since the early solar system, a geological time capsule recording impacts that occurred billions of years ago, when planets were still forming and debris was far more abundant than today. When we look at images of Callisto, we see a surface absolutely saturated with impact craters. Craters of all sizes, from the largest multi-ring basins spanning thousands of kilometers down to small fresh craters just a few hundred meters across, cover nearly every square kilometer of visible terrain. The crater density approaches what planetary scientists call saturation equilibrium, the state where new impacts don't increase the total crater count because they destroy existing craters at approximately the same rate they create new ones. This saturation cratering indicates extreme age. The surface must have been exposed to impacts for billions of years to accumulate this density of craters. And importantly, very little has occurred since to erase or modify these ancient scars. Unlike Ganymede with its grooved terrain representing geological resurfacing, or Europa with its young fractured ice shell, or Io with its volcanoes continuously burying old features, Callisto's surface has remained largely static, a frozen record of the early solar system's violence. The largest features on Callisto are enormous multi-ring impact basins, structures created by truly colossal impacts early in the moon's history. The most prominent is Valhalla, named for the Hall of Slain Heroes in Norse mythology, a sprawling structure centered at 10 degrees north latitude. Valhalla consists of a bright central region about 600 kilometers in diameter, surrounded by concentric rings of ridges extending outward to nearly 2,000 kilometers from the center, with some faint outer rings reaching almost 4,000 kilometers across, roughly half of Callisto's entire diameter. Valhalla formed when an asteroid or comet, probably tens of kilometers in diameter, struck Callisto billions of years ago. The impact released enormous energy, vaporizing the impactor and excavating a huge cavity in the ice. But ice at depth, warmer and more ductile than surface ice, couldn't support this cavity. The floor rebounded, collapsing back upward, while the walls slumped inward. The impact sent seismic waves propagating through Callisto's interior, causing the surface to ripple like a pond disturbed by a stone. These ripples froze into the concentric rings we see today, permanent records of the impact's propagation through the ice. Another large basin, Asgard, shows similar morphology, a bright central region surrounded by concentric rings, though not quite as extensive as Valhalla. Multiple other large impact structures dot Callisto's surface, though many are degraded, their features softened by billions of years of subsequent smaller impacts and slow viscous relaxation of the ice. The presence of these giant basins tells us that Callisto, like all solar system bodies, experienced heavy bombardment early in its history, a period when large impactors were far more common than today. Between the giant basins, every portion of Callisto's surface shows heavy cratering. Craters overlap craters. Larger craters contain smaller craters on their floors and walls. Some craters appear relatively fresh, with sharp rims and visible ejecta blankets, while others are so degraded that they're barely recognizable, just subtle circular depressions in the ice. This range of preservation states allows scientists to establish a relative chronology, understanding which impacts came first and which came later, even without knowing absolute ages. The freshest craters on Callisto show characteristic features of impacts into ice. Central peaks or pit craters in the centers of large impacts form as the ice rebounds after excavation. Terraced walls show where blocks of ice slumped downward during crater formation. Ejecta blankets extend outward from the rim, consisting of material thrown out during the impact, often showing ray patterns where bright, fresh ice excavated from depth has been scattered across the darker surrounding terrain. But most of Callisto's craters are not fresh. They've been modified by subsequent processes, primarily by smaller impacts that have gradually eroded and softened their features. Each new impact ejects material that blankets surrounding terrain, slowly burying older features. Over billions of years, this gardening process has created a regolith layer, broken and fragmented ice mixed with rocky material brought up from depth or delivered by the impactors themselves. The dark coloration of Callisto's surface reflects this ancient processing. The ice is contaminated with non-ice materials, rocky dust, organic compounds, perhaps carbonaceous material delivered by cometary impacts. The long exposure to radiation from Jupiter's magnetosphere has further darkened the surface, creating defects in the ice structure and synthesizing complex organic molecules that absorb light. The result is a surface that reflects only about 20% of the sunlight that falls on it, much darker than fresh ice, which would reflect 60% or more. Despite the heavy cratering, Callisto's surface isn't completely uniform. Spectroscopic observations reveal regional variations in composition and brightness. Some regions appear slightly brighter, perhaps containing more ice relative to contaminants. Other regions show different spectral signatures, indicating variations in the concentration of carbon dioxide, water ice grain, size, or other surface properties. These variations might reflect different ages of exposure, different impact histories, or different amounts of radiation. Processing in different magnetic environments. The preservation of such an ancient surface requires that Callisto has experienced minimal geological activity over its history. The Moon hasn't undergone the tectonic processes that created Ganymede's grooved terrain. It hasn't had volcanic resurfacing like Io or tectonic disruption like Europa. The interior has remained relatively quiet, not generating enough heat to drive significant surface modifications. This geological quiescence is puzzling, given that Callisto is nearly as large as Ganymede and formed from similar materials under similar conditions. The difference must relate to Callisto's thermal evolution. For some reason, perhaps related to its formation conditions or orbital evolution, Callisto never became hot enough early in its history to drive extensive differentiation or geological activity. Or if it did undergo some differentiation, it happened slowly enough that the surface didn't experience the kind of catastrophic resurfacing that would have erased the ancient impact record. The Moon cooled into a stable state that has persisted for billions of years. Looking at Callisto's surface is like looking through a telescope pointed not into space, but into time, seeing a landscape that has changed little since the solar system was young, when planets were still clearing their orbits of debris, when impact rates were orders of magnitude higher than today. The craters are not just geological features, but historical documents, each one recording a specific moment when a specific projectile happened to intersect Callisto's orbit, struck the surface, and left its permanent mark. This ancient witness has watched the solar system evolve, has seen impact rates decline as the planets swept up most of the remaining debris, has orbited Jupiter for more than 4 billion years, while remaining essentially unchanged. The quiet giant, patient in its outer orbit, preserving its scars, offering us a window into epochs otherwise lost to geological activity on more dynamic worlds. As you drift deeper towards sleep, imagine Callisto's surface stretching before you, every horizon showing craters within craters, the accumulated history of billions of years written in ice, a library of impacts waiting to be read, the most ancient face in the solar system, watching, remembering, preserving. To understand why Callisto is so different from Ganymede, despite their similar sizes and compositions, we must look beneath the heavily cratered surface into the Moon's interior structure. What we find there is as surprising and scientifically significant as the ancient surface itself, evidence that Callisto never fully differentiated, never completely separated into distinct layers of rock and ice, remaining instead a partially mixed body, with rock and ice combined throughout much of its interior. Differentiation is the process by which a planetary body separates into layers based on density. When a planet or moon forms, it initially consists of a roughly homogeneous mixture of all the materials that are accreted together: silicate rock, metallic iron, and in the outer solar system, water ice. If the body becomes hot enough, denser materials sink toward the center under their own weight, while lighter materials rise to the surface, creating a layered structure with a dense core, a rocky mantle, and a low-density crust. Earth is fully differentiated, with an iron core, silicate mantle, and light crustal rocks. The Moon is differentiated, having undergone melting early in its history that allowed rock and metal to separate. Even relatively small bodies like large asteroids can show signs of differentiation if they were hot enough early in solar system history. Ganymede, as we've discussed, is clearly differentiated, possessing a liquid iron core that generates its magnetic field. But Callisto tells a different story. The primary evidence comes from measurements of the Moon's moment of inertia, a quantity that describes how mass is distributed within a spherical body. If all of Callisto's mass were concentrated at its center, the moment of inertia would be zero. If all the mass were concentrated at the surface, the moment of inertia would be at its maximum value. Real bodies fall somewhere in between, with the exact value depending on how mass is distributed with depth. NASA's Galileo spacecraft measured Callisto's moment of inertia by tracking tiny perturbations in the spacecraft's trajectory as it passed close to the Moon. The gravitational pull from Callisto depends not just on total mass, but on how that mass is arranged. From these measurements, scientists calculated that Callisto's moment of inertia factor, the moment of inertia divided by the moment for a uniform sphere, equals about 0.355 compared to roughly 0.31 for Ganymede. This difference is significant. Ganymede's lower value indicates substantial concentration of mass toward the center, consistent with a dense iron core surrounded by lighter materials. Callisto's higher value suggests less concentration of mass, indicating that dense materials haven't sunk all the way to the center. The interior appears to be only partially differentiated, with rock and ice remaining mixed throughout much or most of the body. Models that match Callisto's mass, radius, and moment of inertia suggest a structure with perhaps a small rocky core, maybe 400 to 600 kilometers in radius, surrounded by a mixed ice-rock mantle extending most of the way to the surface. In this mixed mantle, ice and rock exist together rather than in separate layers, creating a body with intermediate density throughout rather than the sharp density contrasts we'd expect in a fully differentiated moon. Why would Callisto remain undifferentiated while Ganymede differentiated? The key difference likely relates to heat. Differentiation requires the body to be hot enough for materials to become mobile, for denser materials to sink through lighter materials over millions of years. This requires either substantial heating early in the moon's history or some sustained heat source that keeps the interior warm enough for convection. The heat sources available to forming moons include accretional heating from impacts during formation, decay of short-lived radioactive isotopes like aluminum-26 that were present in the early solar system, and in some cases tidal heating from gravitational interactions with the planet and other moons. For Ganymede, these heat sources apparently combine to make the moon hot enough for differentiation to occur, possibly early in its history, when accretional heating and short-lived isotopes were most important. Callisto, being farther from Jupiter, experienced less tidal heating, both during formation and throughout its subsequent evolution. It also may have accreted more slowly, allowing heat to radiate away during formation, rather than building up to the point where large-scale melting and differentiation could occur. Or perhaps it formed in a region of the proto-Jovian disk, where temperatures were lower, meaning it incorporated more volatile ices that absorbed heat through melting and evaporation, rather than allowing temperatures to rise high enough for differentiation. The lack of complete differentiation has profound implications for Callisto's evolution. Without a dense core sinking toward the center and releasing gravitational energy, without large-scale convection mixing the interior, the moon never experienced the kind of internal heating that drives geological activity. The surface remained cold and static, unable to undergo the tectonic processes that created Ganymede's grooved terrain. This explains why Callisto's surface is so ancient and heavily cratered. Nothing has erased or modified the impact record. But Callisto's story has a twist. Despite the evidence for incomplete differentiation, the magnetic induction measurements from Galileo indicate the presence of a conducting layer within Callisto, most plausibly interpreted as a subsurface ocean. How can a moon possess a liquid ocean without being differentiated? How can water remain liquid in a body that never got hot enough to fully separate? The answer may involve ammonia. Water mixed with ammonia has a much lower freezing point than pure water, potentially remaining liquid at temperatures well below 273 Kelvin. If Callisto's interior contains substantial ammonia, incorporated during formation from ammonia-rich ices in the proto-Jovian disk, this ammonia-water mixture could remain liquid even in a relatively cold, undifferentiated body. The ocean would exist as a layer within the mixed ice rock interior, perhaps 100 to 200 kilometers below the surface. This ocean in an undifferentiated body scenario is unique in the solar system, as far as we know. It suggests that subsurface oceans can exist under a wider range of conditions than we might have thought, not requiring substantial internal heating or complete differentiation. This has implications for the search for habitable environments beyond Earth. Even cold, geologically quiet bodies might harbour liquid water if the right antifreeze compounds are present. The partial differentiation and cold interior also mean that Callisto lacks an intrinsic magnetic field. Without a liquid iron core undergoing convection, There's no dynamo to generate a magnetic field like Ganymede's. The Moon remains unmagnetized, aside from the induced field created by Jupiter's rotating magnetic field interacting with the conducting ocean layer. Understanding Callisto's interior structure remains an active area of research. Future missions with more sensitive gravity measurements could refine our understanding of mass distribution, perhaps detecting layers or variations that current data can't resolve. Seismic measurements, if we could somehow place instruments on Callisto to detect vibrations from impacts or tidal flexing, would reveal interior structure directly, distinguishing between solid and liquid layers, measuring ice thickness, and constraining the ocean's properties. The undifferentiated interior makes Callisto a natural laboratory for understanding planetary formation and evolution. By comparing Callisto to Ganymede, two bodies similar in size and composition but with such different evolutionary paths, we can constrain theories about what conditions determine whether a moon differentiates and becomes geologically active or remains primitive and quiet. The ancient witness, with its mixed interior and frozen surface, stands as testimony to one possible outcome of moon formation, a path taken by this one particular body in this one particular place, offering lessons about how small changes in initial conditions or heat sources can lead to dramatically different evolutionary outcomes over billions of years. Perhaps no discovery about Callisto has been more surprising than the realization that beneath its ancient, heavily cratered surface, within its undifferentiated interior, lies a hidden ocean of liquid water, maintained for billions of years despite the moon's apparent lack of geological activity and internal heat sources. The story of this discovery begins with Galileo's magnetometer data. During close flybys of Callisto in the late 1990s and early 2000s, the magnetometer detected a varying magnetic field that changed depending on Callisto's position relative to Jupiter. The pattern was distinctive and couldn't be explained by an intrinsic magnetic field like Ganymede's, which would remain relatively constant. Instead, the varying field suggested magnetic induction, Jupiter's rotating magnetic field inducing electric currents in some conducting layer within Callisto. For magnetic induction to occur requires a layer that conducts electricity reasonably well. Solid rock and solid ice are both poor conductors at the cold temperatures in Callisto's interior. But liquid water containing dissolved salts conducts electricity readily, well enough to carry the induced currents that create the secondary magnetic field Galileo detected. The characteristics of the induced field, particularly how it varies with Jupiter's magnetic field orientation, allow scientists to estimate the depth and thickness of this conducting layer. Current models place Callisto's ocean roughly 100 to 200 kilometers beneath the surface, similar to Ganymede's ocean depth, but reached through a very different interior structure. Instead of lying between a differentiated ice shell above and rocky mantle below, Callisto's ocean exists within the mixed ice rock interior, perhaps as a global layer, or perhaps as interconnected pockets of liquid in an otherwise solid but partially permeable matrix. The ocean's thickness remains uncertain, but might exceed 100 kilometers, potentially containing a volume of water comparable to or exceeding all of Earth's oceans combined. The depth and thickness depend on the thermal structure of Callisto's interior, which depends on heat sources and thermal conductivity of the overlying materials. Different models with different assumptions produce different ocean characteristics, but all agree that some substantial body of liquid water must exist to explain the magnetic data. The salinity of Callisto's ocean can be estimated from the strength of the magnetic induction signal. Higher salinity means better electrical conductivity, which means a given induced current produces a stronger magnetic field. The data suggests salinity probably similar to Earth's oceans or somewhat higher, perhaps 3 to 10% dissolved salts by mass. These salts likely include sulfates and chlorides leached from rocks in contact with the water, similar to the salt composition in Earth's oceans. But the mystery is, how does this ocean remain liquid? Callisto's surface temperature averages around 130 Kelvin, far below the freezing point of pure water at 273 Kelvin. The interior is warmer, heated by decay of long-lived radioactive isotopes in any rocky materials present. But models suggest the interior temperature isn't dramatically higher than the surface, probably not exceeding 250 to 270 Kelvin at the ocean's depth. Pure water would freeze solid under these conditions. The leading explanation involves ammonia as an antifreeze. A mixture of water and ammonia can remain liquid at much lower temperatures than pure water. A eutectic mixture, the composition with the lowest possible freezing point, consisting of about 32% ammonia and 68% water by mass, remains liquid down to 176 Kelvin, well below the temperatures expected in Callisto's interior. Even with less ammonia, the freezing point depression would be substantial, potentially allowing liquid water to exist at the temperatures models predict for Callisto's subsurface. Ammonia is plausible in Callisto's interior because ammonia ices likely existed in the region where the Galilean moons formed. Ammonia is abundant in the outer solar system, observed in comets and in the atmospheres of the giant planets. When Callisto accreted, it probably incorporated ammonia-rich ices along with water ice and rocky materials. During any partial melting or aqueous alteration that occurred, ammonia would dissolve in the liquid water, lowering its freezing point and potentially allowing that water to remain liquid even as the interior cooled. The presence of ammonia has implications beyond just keeping the ocean liquid. Ammonia is a source of nitrogen, essential for the amino acids that make up proteins in all terrestrial life. If Callisto's ocean contains ammonia, it contains one of the key elemental ingredients for life. Though whether life could actually originate or survive in such an environment remains highly speculative and depends on many other factors like available energy sources and organic compounds. The ocean's stability over billions of years presents interesting questions. Has it existed continuously since Callisto formed, or has it frozen and melted cyclically as the moon's heat production has varied? If the ocean formed early when the interior was warmer, has it been slowly freezing over time as radioactive heat sources have decayed? Or has it reached a steady state where the rate of heat generation equals the rate of heat loss, maintaining a constant ocean thickness indefinitely? Models suggest the ocean is likely stable on billion-year timescales given reasonable assumptions about Callisto's composition and heat production. The thick ice shell above the ocean acts as an insulator, slowing heat loss to space. The ammonia keeps the freezing point low, reducing the required heat flux to maintain liquid. An ongoing radioactive decay, particularly of uranium, thorium and potassium in any rocky materials, provides steady heat input that can balance the losses. The ocean's interactions with surrounding materials remain unclear. Does the ocean contact rock, allowing water-rock reactions that could provide chemical energy and dissolved minerals? Or does it exist entirely within an ice-rich matrix, isolated from direct rock contact? If rock contact exists, does it occur at the bottom of the ocean, similar to Earth's ocean floors, or is rock distributed throughout the region in a mixed ice-rock water matrix? The possibility of chemical reactions at the ocean-rock interface interests astrobiologists. On Earth, hydrothermal systems at ocean spreading centers and in subduction zones support rich ecosystems based on chemosynthesis, organisms that extract energy from chemical reactions rather than from sunlight. Could similar processes occur in Callisto's dark ocean? The moon lacks the tidal heating that might drive vigorous hydrothermal circulation, but even slow water-rock interactions could provide some chemical energy over geological time. The ocean also provides a potential habitat that's protected from the harsh surface environment. Callisto's surface is bombarded continuously by radiation from Jupiter's magnetosphere, making it hostile to any life as we know it. But the ocean, shielded by hundreds of kilometers of ice and rock, receives essentially no radiation exposure. The environment is stable, unchanging, over millions or billions of years, maintaining liquid water in darkness, perhaps with dissolved nutrients from rock contact, perhaps with organic compounds incorporated during Callisto's formation. Whether such an environment could actually host life is unknown and probably unknowable without direct exploration. The ocean is isolated from sunlight, so photosynthesis is impossible. It's isolated from the surface, so organic materials delivered by comets and asteroids can't easily reach it. The energy available from water-rock reactions is probably very limited compared to Earth's hydrothermal systems. And we don't know if life can originate in such an energy-poor environment, or if it requires the kind of energy-rich conditions that apparently existed on early Earth. But the mere presence of the ocean, an unexpected discovery from magnetic field measurements, reminds us that liquid water oceans might be common in the outer solar system, existing not just on geologically active moons like Europa, but also on quiet, ancient moons like Callisto. The requirements for maintaining liquid water are less stringent than we once thought. You don't need vigorous tidal heating or active geology, just some heat source, some insulation, and perhaps the right antifreeze compounds. As you drift towards sleep, imagine that hidden ocean, silent and dark beneath hundreds of kilometers of ice and rock, cold water mixed with ammonia, moving slowly, if at all, perhaps touching rocks at its base where water and mineral might react in slow motion. A sea that has existed longer than complex life on Earth, waiting in patient darkness, one of many secrets the quiet giant keeps beneath its ancient face. Callisto's position as the outermost of the Galilean moons, orbiting Jupiter at a distance of 1,700 kilometers every 16.69 days, places it in a unique, dynamical situation that has profoundly affected its evolution. Unlike Io, Europa, and Ganymede, which participate in the Laplace resonance with its precise 1:4 ratio of orbital periods, Callisto orbits just outside this resonant configuration, avoiding the enhanced tidal heating that affects its inner siblings. A orbital resonance occurs when two or more orbiting bodies exert regular, periodic gravitational influences on each other, due to their orbital periods being related by a ratio of small integers. The Laplace resonance, linking Io, Europa, and Ganymede, is particularly strong because it involves three bodies and creates reinforcing gravitational tugs that maintain the orbital relationships over billions of years. This resonance has profound effects on the inner three moons, particularly on Io and Europa. For Io, the innermost Galilean moon, the resonance maintains its orbital eccentricity, preventing tidal forces from circularizing the orbit. As Io orbits Jupiter on this slightly elliptical path, the distance to Jupiter varies, and so does the strength of Jupiter's tidal force on the Moon. This varying tidal force flexes Io's interior, generating enormous heat through friction. The tidal heating is so intense that Io experiences constant volcanic activity, with hundreds of active volcanoes continuously resurfacing the Moon. Europa also experiences significant tidal heating due to the resonance, though less intensely than Io. This heating keeps Europa's subsurface ocean liquid and likely drives some of the tectonic activity that creates the young, fractured surface we observe. Even Ganymede, farther from Jupiter, receives some tidal heating contribution from the resonance, possibly contributing to the geological activity that created its grooved terrain. But Callisto, orbiting outside the resonance at a distance that doesn't fit into any simple ratio with the inner moon's periods, avoids this enhanced tidal heating. The tidal forces from Jupiter still act on Callisto, but because the Moon isn't locked into a resonance that maintains orbital eccentricity, tides have circularized Callisto's orbit over billions of years. On a nearly circular orbit, the distance to Jupiter remains essentially constant, so the tidal force doesn't vary significantly, and little tidal flexing or heating occurs. This lack of tidal heating has been crucial for Callisto's evolution, or rather, for its lack of evolution. Without the heat input that tidal dissipation provides to the inner moons, Callisto's interior remained colder, preventing the kind of differentiation and geological activity that we see on Ganymede. The Moon never became hot enough to fully separate into layers, never generated the internal heat needed to drive surface tectonics, and thus preserved its ancient surface virtually unchanged for billions of years. The question of why Callisto isn't in the resonance is interesting. The resonance likely formed through orbital migration as the moons interacted gravitationally with the gas disk surrounding young Jupiter and with each other. As moons migrate inward or outward through these interactions, they can be captured into resonances when their orbital periods approach ratios of small integers. The 1-2-4 resonance of Io, Europa, and Ganymede is particularly stable and may have formed early in the system's history. Callisto apparently avoided capture into a resonance with Ganymede that would have extended the chain to a 1-2-4-8 ratio. Perhaps Callisto formed too far out, already outside the region where capture was likely. Or perhaps it did participate in a resonance early on, but escaped through some dynamical interaction or change in Jupiter's environment. Or maybe the resonance tried to form, but the system couldn't stabilize a four-body resonance as readily as the three-body configuration. Whatever the reason, Callisto's position outside the resonance has made it a fundamentally different kind of moon from its inner siblings. It's a control case, showing what a large Jovian moon looks like without the complications of significant tidal heating. By comparing Callisto to Ganymede, we can isolate the effects of tidal heating on moon evolution. Understanding how much of Ganymede's geological activity results from tides versus other heat sources like radioactive decay. Callisto's orbital parameters have implications beyond tidal heating. The Moon's distance from Jupiter means it spends part of its orbit outside Jupiter's main radiation belts, where charged particle densities are highest. While Callisto still receives substantial radiation compared to bodies farther from Jupiter, the exposure is less intense than what Europa or Ganymede experience. This affects the rate of surface processing by radiation and influences the chemistry of surface ices. The orbital period of 16.69 days, substantially longer than the 7.15 days it takes Ganymede to orbit, means Callisto spends more time in different parts of Jupiter's magnetosphere during each circuit. This longer period also means the day-night cycle is longer, with each hemisphere spending more time in sunlight and more time in darkness compared to the inner moons. These differences affect surface temperatures, sublimation rates, and the exosphere density and composition. From Callisto's surface, Jupiter would appear smaller than it does from the inner moons, spanning about 10 degrees of sky rather than the 19 degrees visible from Ganymede. But Jupiter would still dominate the sky, hanging perpetually in the same position for any observer on Callisto's near side, slowly going through phases as Callisto orbits, but never rising or setting. The view would be magnificent, Jupiter's bands and storms visible in detail, occasional auroral displays at Jupiter's poles, and occasionally, if the geometry aligned correctly, the shadows of the inner moons transiting across Jupiter's face. Callisto's orbit is also significant for future exploration. Mission planners have considered Callisto as a potential base for human exploration of the Jovian system, precisely because of its distance from Jupiter and its position outside the most intense radiation belts. A base on Callisto would provide easier access to resources, a more benign radiation environment compared to the inner moons, and a platform for observing and studying the entire Jovian system. The orbital stability of Callisto over billions of years means the Moon has maintained essentially the same relationship with Jupiter and the inner moons throughout solar system history. While the exact orbital parameters have undoubtedly evolved slowly due to tidal dissipation and gravitational interactions, the basic configuration, Callisto orbiting outside the resonance at roughly twice Ganymede's distance, has probably persisted since early in the system's evolution. This stability has allowed Callisto to serve as a faithful recorder of solar system history, preserving impact records that date back to the early epochs when planets were still forming. Understanding Callisto's orbital dynamics and how it avoided resonance capture continues to inform theoretical models of moon formation and migration. The Jovian system serves as a laboratory for studying orbital dynamics, resonance formation, and tidal evolution in multi-body systems. The fact that 4 large moons orbit Jupiter, 3 in resonance and 1 outside, provides multiple data points for testing theories and understanding how such systems form and evolve. As your thoughts slow and your breathing deepens, imagine the orbital dance of the Galilean moons, Io racing around Jupiter every 1.77 days, Europa following at twice that period, Ganymede at 4 times, all locked together in gravitational resonance, their periods forever linked. And farther out, Callisto follows its own path, independent, outside the resonance, orbiting at its own pace without the gravitational coordination that binds its siblings. This orbital independence has made all the difference, allowing Callisto to remain cold and quiet, preserving its ancient face while the inner moons undergo continuous transformation. The quiet giant, patient in its outer orbit, watching its siblings dance their coordinated dance while following its own solitary path around Jupiter, unchanged and unchanging, a witness to epochs the inner moons cannot remember. Callisto orbits within Jupiter's enormous magnetosphere, a region of space dominated by the giant planet's magnetic field and filled with charged particles trapped and accelerated by that field. This magnetospheric environment, while less intense at Callisto's distance than at the orbits of the inner Galilean moons, still subjects Callisto's surface to continuous bombardment by energetic electrons, protons, and heavier ions. Over billions of years, this radiation has profoundly affected the surface chemistry, breaking apart molecules, enabling new chemical reactions, and creating compounds that would never form under normal temperature and pressure conditions. Jupiter's magnetosphere extends millions of kilometers into space, far beyond the orbits of all 4 Galilean moons. The magnetosphere rotates with Jupiter's rapid 10-hour period, creating a rotating flow of magnetospheric plasma that sweeps past the moons. At Callisto's orbit, roughly 27 Jupiter radii from the planet's center, the magnetic field strength has decreased substantially from its values near Jupiter, but charged particles accelerated elsewhere in the magnetosphere still reach Callisto's orbit, particularly during magnetic storms or when the solar wind compresses Jupiter's magnetosphere. The energies of these particles vary widely. Electrons in Jupiter's magnetosphere can have energies ranging from a few electron volts to several million electron volts. Protons and heavier ions show similar energy ranges. The most energetic particles can penetrate into Callisto's surface ice, depositing their energy over the first few micrometers to millimeters of depth. Lower energy particles are stopped at or very near the surface, affecting only the uppermost molecular layers. When a high-energy particle strikes a water ice molecule at Callisto's surface, it can break the molecular bonds, separating the oxygen and hydrogen atoms. This process, called radiolysis, creates free radicals and reactive species that can recombine in various ways. Two hydrogen atoms might combine to form molecular hydrogen, H2, which escapes quickly to space due to its low mass. Oxygen atoms might combine to form molecular oxygen, 2, which can be trapped in the ice or slowly diffuse to the surface and escape into the exosphere. But radiolysis doesn't just break apart water molecules, it also enables the formation of more complex compounds. Hydrogen peroxide, H2O2, forms through reactions involving oxygen radicals and is detected spectroscopically on Callisto's surface. Ozone, O3, can form when energetic particles break apart O2 molecules, creating individual oxygen atoms that then combine with other O2 molecules. These oxygen-rich compounds contribute to the oxidizing chemistry occurring at the surface. The presence of carbon in any form, whether from cometary impacts delivering organic materials or from carbon dioxide ice on the surface, allows even more complex chemistry. Carbon and oxygen can combine under radiation to form carbon monoxide, CO, carbon dioxide, CO2, and various organic compounds. If sulfur is present, delivered perhaps by volcanic materials from Io that have made their way to Callisto's orbit and deposited on the surface, then sulfur compounds like sulfur dioxide, SO2, or various sulfates can form. Spectroscopic observations have detected carbon dioxide on Callisto's surface, particularly in regions that receive enhanced radiation exposure or on the trailing hemisphere, which faces into the direction of orbital motion and thus receives more intense particle bombardment as Callisto sweeps through the magnetospheric plasma. The CO2 might be primordial, incorporated when Callisto formed, or it might be created by radiation processing of carbon-bearing materials over billions of years. The darkening of Callisto's surface, its low reflectivity compared to freshwater ice, results partly from this radiation processing. The breaking and reforming of chemical bonds creates defects in the ice crystal structure, regions where the regular arrangement of water molecules is disrupted. These defects absorb light, making the ice appear darker. Additionally, complex organic molecules created by radiation chemistry tend to be dark, absorbing light across a wide range of wavelengths. Laboratory experiments have simulated Callisto's radiation environment by bombarding water, ice and ice mixtures with high-energy particles similar to those in Jupiter's magnetosphere. These experiments show that irradiated ice develops a dark, reddish-brown coloration over time, becoming darker with increasing radiation dose. The color and spectral properties of the laboratory samples match observations of Callisto's surface reasonably well, supporting the interpretation that radiation darkening is a major process affecting the Moon's appearance. The radiation environment varies across Callisto's surface. The trailing hemisphere, which faces into the orbital motion and thus collides head-on with magnetospheric particles, receives more intense bombardment than the leading hemisphere. This creates an asymmetry in surface composition and darkness, with the trailing hemisphere appearing darker and showing different spectral signatures than the leading hemisphere. Orbital geometry causes this pattern, with charged particles preferentially hitting one side of the synchronously rotating Moon. The poles and equatorial regions also show differences related to radiation exposure. Some models suggest that Callisto might have a weak-induced magnetic field, or that Jupiter's magnetic field configuration might shield certain latitudes more than others, creating patterns in radiation dose across latitude. These patterns would lead to corresponding variations in surface chemistry and appearance, which can be detected through careful spectroscopic mapping. Over billions of years, radiation has processed the surface to substantial depths through the combined effects of direct penetration by high-energy particles and mixing by micrometeorite impacts that turn over the upper layers of regolith, material that was meters below the surface billions of years ago has been excavated and exposed to radiation. Conversely, material currently at the surface will eventually be buried by ejecta from impacts elsewhere. This gardening process creates a well-mixed surface layer in which essentially all the ice has been exposed to radiation at some point. The continuous production of O2 through radiolysis contributes to Callisto's exosphere. Some oxygen molecules escape into the tenuous atmosphere, where they can be detected through ultraviolet spectroscopy. The exospheric oxygen density varies with Callisto's position in Jupiter's magnetosphere and with solar illumination, which affects sublimation rates and photochemistry. The presence of this oxygen exosphere, like Ganymede's, testifies to the ongoing radiation processing of the surface. The radiation chemistry occurring on Callisto has implications for understanding icy moon surfaces throughout the solar system. Similar processes affect Europa, Ganymede, and Saturn's icy moons, each with different radiation intensities and different starting compositions, creating a diversity of surface chemistries. By studying Callisto, where the radiation is less intense than at Europa, but still significant, scientists can calibrate models of radiation processing and understand how surface appearance and composition relate to radiation dose over time. The chemical complexity created by radiation also matters for astrobiology. Radiation can create organic molecules building blocks for life, but it can also destroy them. The balance between creation and destruction depends on the radiation intensity, the presence of shielding, and the availability of carbon and other elements. Understanding this balance helps assess whether radiation-processed surfaces like Callisto's might preserve organic materials delivered by comets, or whether such materials would be quickly destroyed. As you settle deeper into sleep, imagine the invisible rain of particles continuously falling on Callisto's surface. Electrons and protons and ions accelerated to tremendous speeds by Jupiter's magnetic field, striking ice molecules and shattering them, enabling oxygen atoms to find each other and combine, creating peroxide and ozone, breaking carbon dioxide into pieces that reform in new combinations, slowly darkening the ice through billions of years of accumulated damage, writing chemical history in molecular structures, too small to see but detectable through careful spectroscopy. A history of transformation occurring atom by atom, molecule by molecule, across every square centimetre of the ancient surface, the quiet giant bearing not just the scars of impacts, but the accumulated chemical effects of 4 billion years bathed in Jupiter's radiation, patiently accepting each particle, each reaction, each small change, preserving them all in the cold ice, waiting for us to learn how to read the chemical story written there. After decades of waiting, after the end of the Galileo mission in 2003 left us without a dedicated Jupiter orbiter, new spacecraft are finally on their way to study the Galilean moons with unprecedented detail. The Jupiter Icy Moons Explorer, known as JUICE, launched by the European Space Agency in April 2023, is currently making its way across the solar system toward a July 2031 arrival at Jupiter. This mission represents the next generation of Jovian system exploration, carrying instruments designed specifically to answer questions that Galileo raised but couldn't fully address. JUICE's primary targets are Ganymede, Europa, and Callisto, the three large icy moons that show evidence for subsurface oceans. The mission's overarching goal is to characterize these moons as potential habitats, understanding their oceans' properties, ice shell structures, surface compositions, and interactions with Jupiter's magnetosphere. While Io's dramatic volcanism will remain largely unstudied by this mission, the quieter giants will finally receive the detailed attention they deserve. The spacecraft carries 10 sophisticated instruments, each designed to investigate specific aspects of the moon's characters. A high-resolution camera will map surface features at scales down to a few meters, far better than Galileo achieved, revealing details of geological structures and helping identify potential landing sites for future missions. An imaging spectrometer will analyze surface composition, detecting minerals, ices, and organic compounds across a wide range of wavelengths, building comprehensive maps of chemical distribution. A radar sounder, capable of penetrating kilometers into ice, will probe the internal structure of the Moon's ice shells. By measuring how radar pulses reflect from layers within the ice, the instrument can detect boundaries between ice phases, potentially identify liquid water pockets, and determine ice shell thickness at various locations. This capability is crucial for understanding whether and where subsurface oceans exist and for characterizing the ice layers above them. The magnetometer, similar in principle to Galileo's, but with improved sensitivity and modern data analysis techniques, will measure magnetic fields around each moon with unprecedented precision. For Ganymede, it will map the intrinsic magnetic field in detail, helping constrain models of the internal dynamo. For Callisto and Europa, it will measure the induced fields that reveal subsurface oceans, potentially determining ocean depth, thickness, and salinity more accurately than current estimates. A laser altimeter will measure surface topography precisely, creating elevation maps that reveal the shapes of craters, mountains, grooves, and other features. Combined with gravity measurements, topography helps constrain internal structure and understand how the ice shell supports or relaxes topographic features over time. For Ganymede's grooved terrain, detailed topography will help understand the tectonic processes that created these features. The gravity science experiment doesn't require a separate instrument, but uses the spacecraft's radio system. By tracking tiny changes in radio signal frequency as JUICE passes near each moon, scientists can measure variations in gravitational pull that reveal internal mass distribution. These measurements will refine estimates of differentiation, potentially detecting distinct layers within the ice shells or constraining ocean properties through their effects on the gravity field. A particle instrument package will study the charged particles around the moons, measuring their energies, compositions, and spatial distributions. This helps understand how the moons interact with Jupiter's magnetosphere, how particles precipitate into the exospheres to create aurora, and how radiation processing affects the surfaces. For Ganymede, with its intrinsic magnetosphere, these measurements will reveal how the magnetospheric boundaries move and respond to Jupiter's rotating field. An ultraviolet spectrograph will observe exospheres and aurora, detecting oxygen, hydrogen, and other species in the thin atmospheres around the moons. It will study how exospheric density varies with location and time, how aurora respond to magnetospheric conditions, and what these phenomena reveal about surface processes and internal structure. JUICE's mission design involves a complex orbital ballet, arriving at Jupiter and initially spending time studying Io and Europa before gradually reshaping its orbit through multiple flybys of Callisto and Ganymede. The spacecraft will conduct 2 close flybys of Europa, observing this intriguing moon while maintaining distance from Jupiter's most intense radiation. It will then perform numerous flybys of Ganymede and Callisto, building up comprehensive datasets for both moons before the mission's culmination, insertion into orbit around Ganymede itself. In September 2034, if all goes according to plan, JUICE will become the first spacecraft ever to orbit a moon, other than Earth's moon. The Ganymede orbital phase will last roughly 9 months, during which the spacecraft will conduct intensive observations from varying altitudes and orientations. The orbit will gradually decay, bringing JUICE closer to Ganymede's surface, before the spacecraft eventually impacts the surface in a controlled manner, ensuring it doesn't accidentally contaminate Europa if it were to remain in orbit and eventually crash there. The data JUICE returns will revolutionize our understanding of these quiet giants. We'll see surface features at resolutions that rival images from lunar or Martian orbiters. We'll map chemical composition in detail, identifying variations that current observations can only hint at. We'll probe the ice shell's internal structure, potentially detecting liquid layers or measuring ice thickness directly. We'll characterize the magnetic fields and magnetospheric interactions with precision that will distinguish between competing models. For Ganymede, JUICE will help us understand how the groove terrain formed, whether it relates to the magnetic field's generation, and what heat sources powered the tectonic activity. We'll learn whether the subsurface ocean exists as current models suggest, and what its properties might be. We'll map the magnetosphere in detail, understanding how this moon-scale magnetic bubble operates within Jupiter's planetary scale field. For Callisto, JUICE will help confirm the subsurface ocean's existence and characterize its properties. We'll learn whether the interior is truly undifferentiated or whether there's more structure than current data reveal. We'll understand better how an ocean can persist in such a geologically quiet body and whether ammonia is indeed present as an antifreeze. We'll map the ancient surface in detail, reading the impact history and understanding what it tells us about the early solar system. JUICE isn't traveling alone. NASA's Europa Clipper mission, launched in October 2024, will arrive at Jupiter in April 2030, slightly ahead of JUICE. While Clipper focuses primarily on Europa, conducting dozens of close flybys of that fascinating moon, it will also observe Ganymede and Callisto during flybys used to adjust its orbit. The two missions will overlap at Jupiter, offering opportunities for coordinated observations and complementary data sets from different perspectives. Together, JUICE and Europa Clipper represent an investment of billions of dollars and decades of work by thousands of scientists and engineers across multiple continents. They embody humanity's commitment to exploring these distant worlds, to understanding our solar system's diversity, and to answering fundamental questions about where liquid water exists and whether habitable environments might be common beyond Earth. As these spacecraft travel toward Jupiter, still years away from arrival, our knowledge of Ganymede and Callisto comes primarily from Galileo's data, now 2 decades old, supplemented by ground-based and Hubble observations. We've learned much, but many questions remain open, waiting for new data to definitively answer them. The quiet giants have been patient with us, orbiting Jupiter for billions of years, and they'll remain patient for a few more years as our latest emissaries make their way across the solar system to study them. The anticipation builds slowly, like sleep approaching. Systems are tested, trajectories refined, instruments calibrated. The spacecraft sail through the darkness, propelled by gravity, assists and careful orbital mechanics, carrying our questions toward distant ice worlds that have waited so long to be truly understood. The next chapter of exploration approaches, not yet here but inevitable, bringing us closer to these moons, closer to their secrets, closer to understanding what makes each world unique, and what common principles govern all the moons and planets of our solar system. As we come to the end of our journey tonight, here on Whispering Universes, let's reflect on what Ganymede and Callisto teach us about the nature of worlds, about patience and preservation, about the hidden complexity that waits beneath surfaces that seem simple at first glance. These are the quiet giants, the largest moons in our solar system, save Titan, substantial worlds that would count as planets if they orbited the Sun directly. Yet they've spent billions of years in Jupiter's shadow, following their appointed orbits, changing so slowly that to human eyes they would seem eternal and unchanging. They don't erupt like Io, they don't crack and fracture like Europa, they simply exist, ancient and patient, keeping their secrets beneath kilometers of ice. But as we've discovered through decades of patient observation, through spacecraft missions and theoretical models, through careful measurement of magnetic fields and gravitational perturbations, these quiet moons are far from simple. Ganymede generates its own magnetic field, the only moon known to do so, revealing an active core deep within. Its surface shows the scars of tectonic activity, grooved terrain recording episodes when the ice shell pulled apart and renewed itself. Beneath that ancient surface lies an ocean, liquid water kept warm by heat from the interior, a hidden sea larger than all of Earth's oceans. Callisto preserves the solar system's most ancient face, craters upon craters, recording 4 billion years of impact history unmodified by later geological activity. Yet it too hides an ocean, maintained by antifreeze in an undifferentiated interior that never quite separated into distinct layers. The most primitive-looking moon hosts liquid water, teaching us that oceans can exist under conditions far more diverse than we initially imagined. Both moons possess tenuous exospheres, oxygen released from ice by radiation, creating atmospheres thin as a whisper but detectable by sensitive instruments. Both orbit within Jupiter's enormous magnetosphere, subjected to continuous particle bombardment that modifies their surfaces atom by atom, molecule by molecule, creating chemical complexity through billions of years of accumulated effects. These moons remind us that first impressions deceive, that surfaces tell only part of a story, that patient observation and careful measurement reveal truths invisible to casual viewing. They teach us that worlds evolve in unexpected ways, that small differences in initial conditions or orbital positions can lead to dramatically different evolutionary paths, that even similar-sized bodies formed from similar materials in the same system can become fundamentally different kinds of worlds. As you drift towards sleep, your breathing slowing, your thoughts becoming less distinct. Imagine standing on one of these quiet giants, perhaps on Callisto's ancient surface near the edge of Valhalla, that enormous impact structure, recording a collision from billions of years ago when the solar system was young and violent. The surface stretches before you, cratered and dark, every direction showing the accumulated scars of ancient impacts. Above you, Jupiter dominates the sky, its bands and storms slowly shifting, auroral displays occasionally lighting its poles. The surface is silent, no wind to disturb the ice, no sounds except perhaps the occasional creak of ice adjusting to temperature changes or the distant inaudible thump of a micrometeorite impact. The radiation is invisible but present, particles continuously falling from Jupiter's magnetosphere, striking the ice, breaking molecules, enabling chemistry, slowly, imperceptibly darkening the surface over millions of years. Beneath your feet, deep below, an ocean moves in total darkness. Water that has been liquid for billions of years, kept from freezing by ammonia and by heat from the interior, cold and dark and still, perhaps touching rocks at its base where slow chemical reactions occur, perhaps completely isolated within mixed ice and rock, a sea that has never known sunlight, never known life as far as we know, but liquid nonetheless, patient in the darkness beneath the ice. The universe is full of such places, we're learning. Hidden oceans in unexpected locations, maintained by mechanisms we're only beginning to understand. Worlds that seem quiet and simple, but reward careful study with revealed complexity. Ganymede and Callisto, the quiet giants, have been patient teachers slowly revealing their secrets over centuries of observation, from Galileo's first telescopic glimpse to Galileo spacecraft's detailed reconnaissance to JUICE's upcoming arrival. They'll continue orbiting Jupiter long after humans have visited them, studied them, perhaps even established outposts on their surfaces. They'll remain patient and ancient, preserving their impact records, hiding their oceans, maintaining their slow, magnetic dances with Jupiter's field, watching the cosmos with the patience of worlds that measure time in billions of years. Thank you for exploring these quiet giants with us tonight, here on Whispering Universes. Like and subscribe to join us for future journeys through the cosmos. Let the image of those distant ice worlds, ancient and patient, carry you gently towards sleep. Dream of hidden oceans and ancient craters, of magnetic fields and thin atmospheres, of worlds that wait in silence, keeping their secrets, watching Jupiter's storms, orbiting through the endless night. Sleep peacefully, dream deeply. Remember gently, the quiet giants watch and wait, as they have for billions of years, as they will for billions more.